Hello there, and welcome to Science for Sleep, where curiosity drifts softly and science moves at the speed of calm. Tonight's quiet exploration is about something that doesn't just surround us, but carries us along with it. It's the invisible expansion of everything, the slow, patient stretching of the universe itself. It's a story that began long before stars were born, and one that will continue long after the last one fades. You might have looked up at the night sky before, perhaps while waiting for sleep, and felt that stillness. But the strange truth is that the universe has never really been still. It's been breathing out for billions of years, expanding quietly in all directions, like the slow exhale of creation itself. And somewhere, in the midst of that motion, here you are, listening, existing, part of that same grand unfolding. Before we wander too far into the cosmos, I'd love to know, where in the world are you listening from tonight? Are you hearing this in the calm of evening, maybe with a faint light glowing by your bedside, or on a quiet morning where the day hasn't quite begun yet? Wherever you are, the universe around you is expanding at this very moment. Every atom, every galaxy, every thread of space itself is stretching. It's not something you can see or feel, but it's happening nonetheless. And that's what we're going to explore together tonight. The gentle mystery of an expanding universe, and the question that follows it like a shadow. Will it ever stop? If you find these cosmic wanderings soothing or thought-provoking, a simple like or a quiet subscribe helps this little space reach others who might need a moment of calm too. Think of it as passing along a small pocket of stillness in a very fast world. Now let's slow things down, settle your thoughts, and take a slow breath in. As you exhale, imagine that the universe is exhaling with you, because in a way, it is. When cosmologists describe expansion, they often say that space itself is stretching. That phrase can sound abstract, but think of it like this. Imagine tiny dots drawn on the surface of a balloon. As the balloon inflates, the dots move away from each other, not because they're moving across the surface, but because the surface itself is expanding. That's what's happening on a cosmic scale. Every galaxy is like one of those dots, carried along by the expansion of space itself. It's not that galaxies are flying away through space, it's that space is creating more of itself between them. This idea was once almost unthinkable. For most of human history, we imagine the universe as static, eternal, unchanging. The stars above looked the same every night. The constellations rose and set with comforting regularity. To early astronomers, there was no hint that the cosmos might be in motion. But all that began to change in the early 20th century when a few patient observers started noticing something strange. At a mountaintop observatory in California, a young astronomer named Edwin Hubble spent countless nights studying the faint smudges of light captured by his telescope. These smudges were galaxies, vast collections of stars far beyond our own Milky Way. By analysing their light, Hubble discovered that most of these galaxies were moving away from us, and not just by chance. The farther away a galaxy was, the faster it seemed to be receding. This wasn't random motion. It was a pattern, a rhythm written across the sky. The universe, it turned out, was expanding. It's hard to overstate how revolutionary that discovery was. The very fabric of the cosmos wasn't static after all. It was stretching. Hubble's data was like hearing for the first time the faint heartbeat of the universe. The more scientists studied it, the clearer it became that this wasn't just local motion or a trick of perspective. It was everywhere, in every direction. The universe itself was growing larger. That realization reshaped everything we thought we knew about existence. If the universe is expanding now, it must once have been smaller, denser, hotter. And if you trace that expansion backward in time, you eventually reach a beginning, a moment when everything we see, every galaxy, every atom, was compressed into a single point of almost infinite density and energy. From that unimaginable state, something extraordinary happened. space began to expand. That moment is what we now call the Big Bang. The name Big Bang might make you picture an explosion, something loud and fiery like a cosmic firework. But the reality is quieter and more elegant. There was no explosion in space. There was the expansion of space itself. There was no center, no edge, no blast wave racing outward. Instead, the entire universe was everywhere at once, growing from within, a cosmic swelling. In that sense, it's closer to a breath than a bang, the first great inhale of reality itself. That expansion has never stopped. For over 13 billion years, space has been stretching. Galaxies have drifted apart. Light from distant stars has been stretched along with it, its wavelength elongated, turning visible light into the deep red hues of the cosmic background radiation. That light, still travelling toward us today, carries the faint afterglow of the universe's birth. It's everywhere, a soft whisper from the beginning of time. You can almost imagine it. A universe once hot enough to forge the first atoms, cooling slowly as it expanded, forming stars, galaxies, and eventually us. Every breath you take now carries atoms that were once compressed in that early cosmic furnace. You, right now, are part of the universe's expansion story, not separate from it, but woven into it. When we talk about the universe expanding, it's easy to think of it as something happening out there, beyond the stars, beyond what we can see. But in reality, it's happening everywhere. The space between galaxies is stretching, yes, but so is the space between distant clusters, and even the space within the faint cosmic web that connects them. Yet, on smaller scales, like within galaxies or solar systems, gravity holds things together tightly enough to resist expansion. That's why your room, your planet, your atoms aren't drifting apart. Expansion happens on scales where gravity grows weak, in the vast dark between galaxies. So, as you lie there listening, somewhere far beyond the reach of our telescopes, galaxies are gliding gently away from each other, carried along on the expanding sea of space. And that brings us to the question that quietly hums beneath all of this. Will it always be that way? Will the universe keep expanding forever? Or someday will it stop, maybe even reverse? To even begin to answer that, we have to understand what's guiding the expansion now. When Hubble first made his discovery, scientists assumed that gravity, the great cosmic glue, would eventually slow the expansion down. After all, everything that has mass attracts everything else. Over time, that attraction should pull galaxies toward each other, slowing the universe's growth. But as measurements improved, something unexpected emerged. The universe wasn't slowing down, it was speeding up. Imagine tossing a ball into the air and watching it not fall back, not even coast upward at the same pace, but begin accelerating faster and faster away from your hand. That's what the universe is doing. The space between galaxies isn't just expanding, it's expanding faster and faster as time goes on. This discovery was made in the late 1990s, when two teams of astronomers studying distant supernovae, dying stars that explode with predictable brightness, found that those explosions were dimmer than expected. The light had travelled farther than it should have, meaning the universe had expanded more than anyone predicted. Something was pushing it to accelerate. Scientists gave this mysterious force a name: dark energy. A placeholder, really, for something we still don't understand. Dark energy appears to make up about 70% of the total energy content of the universe, yet it's invisible, intangible, and almost completely unknown. It acts like a kind of pressure, an anti-gravity of sorts, driving space to expand faster over time. And because its effects increase as the universe grows, it's like a runaway process. The more space there is, the more room there is for dark energy to do its work. For now, dark energy seems to be winning. The galaxies are drifting apart faster than gravity can pull them back. And if this continues indefinitely, then the universe will keep expanding forever, growing colder and emptier with each passing eon. Stars will burn out, galaxies will fade from view, even the faint background radiation will stretch into wavelengths too long to detect. The universe would end not with a bang or a collapse, but with a sigh, a slow fading into darkness. But before we drift too far into that distant future, there's something deeply human about even asking this question. We live for such a short span, and yet we wonder about the lifespan of everything. We measure our days and hours, and then we lift our eyes to measure the cosmos, to wonder when it began and when it might end. There's comfort in the rhythm of it, beginnings and endings, expansion and stillness, birth and rest. When you think about it, the universe doesn't just expand out there in space, it expands in us too, in our understanding, in our imagination. Every new discovery stretches the boundaries of what we know, like the cosmos itself teaching us to breathe a little deeper, think a little farther, dream a little wider. And yet, there's still so much we don't know. What exactly is dark energy? Is it constant, or could it change over time? Could it one day fade, allowing gravity to regain control? Could the universe slow down, stop expanding, and begin to contract? These are not just distant scientific curiosities. They are real, ongoing mysteries that keep the world's brightest minds awake at night, staring at data, running simulations, and quietly asking, what if? If the expansion ever does stop, it wouldn't happen suddenly. It would be a cosmic shift that unfolds over billions upon billions of years. The first hints would come not from the stars we see, but from the way space itself behaves. Galaxies might begin to drift more slowly. The light from distant supernovae would change its pattern. And deep in the mathematics of cosmology, the equations describing the universe's fate would start to bend in a new direction. For now, all the evidence points to continued expansion. The universe is growing faster, not slower. But cosmology has a way of humbling certainty. Just a century ago, most scientists believed the cosmos was static. Then it wasn't. A few decades later, they believed expansion must be slowing. Then it wasn't. And now, as we map the faintest whispers of the early universe and measure its acceleration with ever greater precision, we may yet find new surprises waiting in the dark. The question of when or whether expansion will stop is really a question about what the universe is made of, and how those ingredients behave over time. Matter, energy, gravity, and that elusive dark energy all play their parts in this cosmic balancing act. If dark energy stays constant, the universe will expand forever. If it changes, even slightly, the story could end very differently. And that uncertainty, rather than making the universe frightening, makes it endlessly fascinating. Some nights, astronomers sit beneath the dome of a telescope, watching faint galaxies shimmer on their screens. Those galaxies are ancient, their light having travelled billions of years to reach us. Looking at them is like peering into the past, but hidden within that light are clues about the future, how fast the universe is expanding, how it has changed, and maybe how it will all end. In that sense, every observation is a kind of time travel, a glimpse of both what was and what might be. And so, as the night stretches on and the universe continues its quiet expansion, we drift with it, small, temporary, but part of something vast. The universe breathes out, and we breathe with it. The stars above us were born from that expansion, and every atom in our bodies was forged in its aftermath. We are not separate from the cosmic story. We are the story written in matter and motion, carried along on the same expanding sea. So as we keep following this thread through the darkness, let's stay with the question a little longer. What does it mean for a universe to expand? How do we know it's happening? And how did we first discover that space itself is growing, even when everything around us feels still? When we look up at the night sky, it feels like everything above us has always been there. The stars appear pinned in place, the constellations fixed, the great band of the Milky Way unchanging. For most of human history, that illusion of stillness shaped how we imagined the universe. The heavens were thought to be eternal and unmoving, a grand stage on which the small dramas of human life played out beneath the same familiar lights. It wasn't that people lacked curiosity. They simply lacked reason to believe the cosmos itself could move. The stars didn't drift noticeably over a lifetime, and the sky's daily motion was neatly explained by the turning of the Earth. The universe, it seemed, was serene, permanent, and perfectly content to stay that way. But somewhere in that stillness, a few patient minds began to notice faint whispers of motion. A comet would appear, cutting through the heavens and then vanishing. Planets, those wandering stars, would trace strange paths through the constellations, moving against the backdrop of the fixed stars. Even so, no one imagined that the fabric of space itself could expand. It was an idea too strange to fit into any philosophy or theology of the time. By the late 19th century, however, astronomy was undergoing a quiet revolution. Telescopes had become powerful enough to reveal that the soft clouds of light scattered across the sky, those faint smudges known as nebulum, were more than just nearby clouds of gas. Some astronomers began to suspect that they were, in fact, island universes, vast collections of stars far beyond our own Milky Way. The idea was controversial. Many believed the Milky Way was the entire universe, and those nebulae were simply part of it. There was no agreement and no definitive way to measure such distances. But change was coming, and it would begin with the light itself. Light, as it turns out, carries stories. When starlight passes through a prism or a spectrograph, it spreads into a rainbow, a spectrum, crossed by tiny dark lines. These lines are like fingerprints, each marking the presence of specific elements in the star's atmosphere. Hydrogen, helium, oxygen. Every element leaves a distinctive pattern. By comparing those patterns with those observed in laboratories on Earth, astronomers could tell what stars were made of. But something else was hidden in those lines. If the lines were shifted slightly toward the red end of the spectrum, it meant the light waves had been stretched, redshifted. If they were shifted toward the blue, the waves had been compressed, blue-shifted. And that shift meant motion. A red shift showed that an object was moving away. A blue shift meant it was coming closer. It was an elegant discovery. By studying starlight, you could measure cosmic motion without ever leaving Earth. It was like hearing the universe's version of a Doppler effect. The same way the pitch of a siren changes as it passes by, light changes colour depending on whether its source is approaching or receding. At first, astronomers applied this to nearby stars. The results were subtle, but meaningful. Then, attention turned to those mysterious nebulae, those smudges whose true nature was still debated. In 1912, an American astronomer named Vesto Melvin Slipher pointed his spectrograph at the Andromeda Nebula. What he found astonished him. The spectral lines were strongly shifted toward the blue. That meant the nebula was moving toward us, fast. Over the next few years, Slipher repeated his measurements for dozens of other nebulae. Most of them, however, were not coming toward us. They were moving away and at staggering speeds, hundreds or even thousands of kilometers per second. It was one of the first hints that the universe might not be as still as it seemed. But Slipher, cautious and meticulous, didn't leap to conclusions. He simply presented the data, line after line of spectra, velocities neatly listed, and left the deeper meaning for others to uncover. Meanwhile, in Belgium, a young priest with a passion for physics was thinking about the cosmos in mathematical terms. His name was Georges Lemaitre. Drawing on Albert Einstein's recently published theory of general relativity, Lemaitre began to explore what those equations said about the universe as a whole. To his surprise, they didn't describe a static cosmos. They allowed, even demanded, a universe that changed, one that could expand or contract over time. When Lemaitre combined his theoretical insights with Slipher's observations, a remarkable picture began to emerge. If most galaxies were receding, and if the equations of relativity supported it, then perhaps the universe itself was expanding. Lemaitre's ideas were bold, but in 1927 they attracted little attention. The notion of an expanding universe was still too radical. Even Einstein initially dismissed it. He had adjusted his equations years earlier to force them into describing a static universe, introducing something he called the cosmological constant, a mathematical tweak to keep the cosmos from collapsing under its own gravity. When Lemaitre showed him his model, Einstein reportedly said, "Your calculations are correct, but your physics is abominable." Still, Lemaitre was undeterred. He believed the math, and more importantly, he believed the evidence hiding in the light of distant galaxies. Just a few years later, across the Atlantic, Edwin Hubble began to assemble the final pieces. Working at the Mount Wilson Observatory in California, he used the 100-inch Hooker telescope, the largest in the world at the time, to measure the distances to galaxies. To do this, he relied on a special kind of star called a Cepheid variable, which pulses in brightness at a regular predictable rate. By comparing how bright such a star appears from Earth to how bright it truly is, you can calculate how far away it must be. It was one of the cleverest cosmic yardsticks ever discovered. When Hubble plotted the distances of galaxies against their velocities, the speeds that Slipher had measured years earlier, a clear pattern appeared. The farther away a galaxy was, the faster it was moving away. It wasn't a random scatter. It was a straight line, a relationship so precise that it could only mean one thing. The universe itself was expanding. That simple graph, distance on one axis, velocity on the other, changed everything. The slope of that line became known as the Hubble constant, a measure of how fast the universe expands. For the first time, humanity had numerical proof that the cosmos was not static, not eternal, not fixed. It was growing, stretching, evolving. Space itself was expanding between galaxies, carrying them apart like leaves drifting on an ever-widening pond. At first, not everyone was ready to accept it. Einstein himself visited Hubble in 1931 and, after seeing the evidence, reportedly admitted that his earlier assumption of a static universe had been wrong. "That was the greatest blunder of my life," he said of the cosmological constant. Later, physicists would reintroduce that same constant to explain dark energy, a reminder that in cosmology, today's blunder can become tomorrow's breakthrough. Once the reality of expansion was accepted, new questions blossomed almost immediately. If the universe was expanding, when did it start? What was it expanding from? And how long would it continue? The idea of an expanding universe implied a beginning, a moment of creation, and that notion carried profound philosophical weight. It meant the cosmos wasn't eternal in the past. It had a birth. For Lemaitre, who saw no conflict between faith and science, this was deeply moving. For others, it was unsettling. A beginning suggested an origin, and perhaps something beyond physics itself. But in the language of science, the beginning was simply the moment when density and temperature were highest, the moment the equations could trace no further. In the decades that followed, astronomers refined their measurements. They observed more galaxies, better calibrated their cosmic yardsticks, and found that the expansion wasn't just a simple outward drift. Space was stretching uniformly in all directions, but local gravitational clumps, clusters and superclusters created beautiful patterns. The universe resembled a vast web, with galaxies strung along filaments of dark matter and enormous voids between them. On the larger scales, it was surprisingly smooth, as though the cosmos had been gently stirred in its earliest moments. That pattern held another secret. If the universe was expanding, then in the past it must have been denser and hotter. The equations of relativity predicted that the leftover radiation from that early hot phase should still exist, cooled and stretched by billions of years of expansion. And in 1965, two radio engineers, Arno Penzias and Robert Wilson, stumbled upon it. They were testing a microwave antenna and kept finding a persistent background noise no matter where they pointed it. It turned out to be the faint afterglow of the Big Bang itself, the cosmic microwave background radiation. It was the sound of the universe's birth still echoing through space. That discovery confirmed the expanding universe beyond any doubt. It meant the cosmos had indeed begun as a hot, dense state, and had been cooling and stretching ever since. From that moment on, cosmology became a precision science. Astronomers could measure the rate of expansion, estimate the age of the universe, and trace the formation of galaxies over billions of years. Even so, expansion is a subtle thing. It's not something we can see directly with the naked eye. The stars in our sky won't drift apart in any noticeable way during a human lifetime. Even over millennia, constellations change only slightly. But across cosmic distances, the effect becomes undeniable. Galaxies that were once close enough to interact are now separated by millions of light years. The universe itself has grown by a factor of thousands since its earliest moments, and yet the picture is far from complete. When astronomers measure the expansion rate using nearby galaxies and supernovae, they get one value. When they measure it using the cosmic microwave background, essentially the early universe, they get a slightly different one. This mismatch, known as the Hubble tension, has become one of modern cosmology's most intriguing puzzles. It could mean that our understanding of dark energy is incomplete, or that something new and unexpected is happening in the universe's first few billion years. It's as though the cosmos is whispering a riddle, one that we haven't yet learned how to interpret. For now, what we do know is that the universe is expanding, and has been since its beginning. Every observation, from the redshift of galaxies to the background radiation to the clustering of matter, confirms it. And that expansion isn't slowing, it's accelerating. Somewhere in the mathematics of relativity and quantum physics lies the reason why, a mystery that points toward dark energy, the unseen force that fills the cosmos. It's humbling to think that all of this, the galaxies drifting apart, the faint background hum of ancient light, the delicate balance between gravity and expansion, was first uncovered by a few people staring through telescopes and measuring light on photographic plates. They couldn't see the expansion directly. They simply trusted the evidence written in starlight, and from it they uncovered the movement of the universe itself. That movement continues tonight. Somewhere, a photon that left a distant galaxy billions of years ago is just now arriving at Earth, sliding gently into a detector at the edge of an observatory's mirror. Its wavelength has stretched over unimaginable distances, a silent record of space expanding along its path. That one piece of light carries within it the entire story. A universe in motion, a universe that grows, a universe that has never truly been still. And as we keep tracing that motion further, we begin to see the deeper patterns, how galaxies cluster, how cosmic filaments weave together, how dark energy threads through it all. The expansion of the universe isn't just a matter of distances and velocities, it's the rhythm that underlies everything we know. It shapes the way galaxies form, how stars live and die, even how the cosmic background cools. To understand the universe's motion is to understand its heartbeat. As the universe continues its quiet stretching all around you, it's enough to simply rest in the thought that motion is not chaos. It's the natural state of everything. The galaxies move not because they must escape something, but because space itself invites them to drift. And in that slow, endless motion there's a kind of peace, the calm of a cosmos that breathes. If you step outside on a clear night, away from the glow of streetlights, the sky feels infinite. The air cools, the noises of the world fade, and above you stretches a dome of soft darkness scattered with stars. They shimmer, ancient and silent, their light crossing unimaginable distances to reach your eyes. To most people it looks still, eternal, but that stillness is only an illusion. The universe is moving, not quickly, not loudly, but ceaselessly. Every point of light you see is participating in the slow, patient unfolding of space itself. And even though it feels still, the night sky is changing in ways we can't directly see. The distances between galaxies are increasing. The very fabric of the cosmos is stretching. You might imagine that if the universe is expanding, you should be able to see it. Galaxies drifting apart, constellations spreading wider, stars inching away. But human lifetimes are too brief for that. The scale of cosmic motion makes our years, even our centuries, too short to register its movement. Expansion happens at the level of the universe itself. Between galaxies, space grows. Within galaxies, gravity holds matter together so tightly that expansion is negligible. So the sky we see each night, filled with its familiar patterns, is frozen in time from our perspective. Yet over cosmic ages, those patterns will change, and the view from Earth will not always be what it is now. The term astronomers use to describe this cosmic stretching is redshift. It's a small, elegant concept that contains the entire story of expansion. When a galaxy moves away from us, the light it emits is stretched as it travels through expanding space. Its wavelength grows longer, shifting toward the red end of the spectrum. The farther away the galaxy is, the greater the redshift. This effect gives us a way to see motion across the cosmos without ever leaving our tiny planet. Imagine the light from a distant galaxy, perhaps one that left its stars when the Earth was still molten and the first oceans hadn't yet formed. As that light crosses space, it rides the currents of expansion. The waves stretch, elongate, and by the time they reach us, they carry the signature of the universe's growth. Every photon arriving in our telescopes carries a record of how much space has expanded during its journey. That's what makes the night sky so remarkable. It's not just a view of space, it's a view of time. When you look at a nearby star, you're seeing it as it was years ago. When you look at a galaxy a million light years away, you're seeing it as it was a million years ago. The light from the most distant galaxies we've ever observed left them more than 13 billion years ago, when the universe was still young. Those galaxies aren't just far away. They're ancient memories written in light, still arriving after all this time. The sky, in that sense, is a cosmic diary. Every twinkle, every faint shimmer is a message from the past. To understand just how much the universe has expanded, think of how light itself behaves. A photon doesn't age or tire as it travels, it simply moves at the speed of light, following the geometry of space. But if space expands while that photon is in transit, the distance between each crest of its wave grows. It's as if the universe gently pulls the light apart, not violently, but continuously, effortlessly, like taffy stretching over eons. This is why distant galaxies look redder and fainter than they truly are. Their light has been stretched thin by the expansion of space. Astronomers use this cosmic redshift as a kind of ruler. By measuring how much the light has been stretched, they can estimate how far away the source is and how long ago the light began its journey. When Edwin Hubble and his colleagues first plotted those measurements, they noticed that the farther a galaxy was, the greater its redshift. That pattern is what revealed the expansion of the universe in the first place, and even now, decades later, every observation continues to confirm it. But the expansion isn't uniform in the way you might imagine. It's not that galaxies are flying outward from a central point, like sparks from an explosion. There is no center, and there is no edge. Expansion happens everywhere at once. Every region of space stretches equally in all directions. From any point, you would see the same thing. Galaxies moving away, the farthest ones receding fastest. If you lived in another galaxy, you'd see the same pattern we see from Earth. That's one of the quiet wonders of cosmology. No matter where you are in the universe, it looks roughly the same on a large enough scale. It's a difficult idea to picture because our minds are tuned to smaller scales, to horizons, boundaries, beginnings, and ends. But the universe doesn't expand into something. It simply creates more space as it grows. That's one of the most counterintuitive aspects of cosmology. We tend to think of expansion as movement through space, but it's actually the growth of space itself. The galaxies are mostly staying where they are relative to the space around them. It's the space between them that's increasing. That realization changes how you see the night sky. When you gaze upward, you're not looking at a static map of stars and galaxies. You're seeing the frozen frame of an ongoing motion, a cosmic dance that has been unfolding since the beginning. The light that reaches your eyes tonight began its journey when the universe was smaller, denser, younger. As you watch, new light continues its long journey toward the future. Every night sky is both a snapshot and a continuation of that same story. The expansion also gives us a kind of cosmic yardstick, a way to measure the age of the universe itself. If we know how fast it's expanding today, and how that rate has changed over time, we can rewind the cosmic clock and estimate when it all began. The current best estimates put the age of the universe at around 13.8 billion years. That number isn't arbitrary. It's written in the data, in the redshift of galaxies, the temperature of the cosmic microwave background, and the way galaxies cluster together. Everything points to the same remarkable timeline. When astronomers map the universe, they often describe it as a kind of three-dimensional fabric that's been stretching since the Big Bang. Embedded in that fabric are the galaxies, stars, and clusters that make up the visible universe. The pattern we see today, the web of filaments and voids, is the fossil record of how matter responded to expansion and gravity over billions of years. In the densest regions, gravity slowed expansion enough for matter to clump together, forming galaxies and stars. In emptier regions, expansion continued unhindered, leaving behind vast voids. The result is a cosmic structure that's both beautiful and intricate, shaped by the same forces that drive its expansion. You might wonder, if everything is moving away, why aren't we moving too? The answer lies in gravity's local hold. On small scales, gravity overpowers expansion. Within a galaxy, the mutual attraction between stars keeps everything bound together. Within the solar system, the sun's gravity dominates so completely that the expansion of space is negligible. Even your own body is bound by forces far stronger than any cosmic stretching. Expansion is a large-scale phenomenon, something that only becomes noticeable when you measure the universe across hundreds of millions of light years. Still, the idea that the universe is growing even as we live our everyday lives has a strange comfort to it. It's a reminder that stillness is an illusion, that even in the most tranquil night, everything is in motion. The galaxies drift, the stars evolve, and the fabric of space continues to stretch, carrying time and matter forward. You might not feel it, but you're moving with it. Every second, every breath, every heartbeat taking place in a universe that is expanding all around you. This motion has consequences for how the future sky will look. In billions of years, the expansion will carry most galaxies so far away that their light will never reach us again. They'll slip beyond what astronomers call the cosmic horizon, the boundary of the observable universe. Future observers, perhaps living in some distant epoch, might look up and see only the stars of their own galaxy, unaware that others ever existed. To them, the universe will appear static once more, just as it did to us before Hubble's discovery. The expansion will still be happening, but its evidence will have drifted beyond sight. That possibility gives our current view of the sky a certain poignancy. Right now, we exist in a special moment, one when the universe is old enough for galaxies and life to have formed, but still young enough that we can see the evidence of its beginning. We can observe the afterglow of the Big Bang, measure the expansion rate, and map the cosmos on grand scales. We can see far enough to piece together the universe's story. Future civilizations may not have that luxury. To them, the sky might tell a different tale, one of isolation, a single galaxy adrift in darkness. For now, though, the sky remains rich with motion, even if it moves on timescales beyond our grasp. The faint smears of distant galaxies are snapshots of an expanding cosmos. The deeper we look, the further back in time we see, and the more clearly the pattern of expansion reveals itself. With every improvement in our telescopes, we're not just seeing farther, we're seeing the past more vividly, catching the universe in earlier moments of its endless unfolding. In recent years, space telescopes like Hubble and its successor, the James Webb Space Telescope, have looked deeper than ever before, capturing galaxies from when the universe was only a few 100 million years old. Those galaxies appear small and irregular, clumped together, still forming their first stars. Their light, stretched by billions of years of expansion, arrives in infrared wavelengths. Invisible to our eyes but rich with information, it's as if the universe keeps a record of its own childhood, written in light that only now is reaching us. That's what makes the expanding sky such a profound idea. It means that the cosmos is not just a place, but an evolving story. The light above us isn't static decoration. It's a record of motion, of growth, of the passage of time on the grandest scale imaginable. Every observation we make adds another page to that story. And though we can't see expansion happen in real time, we can feel its presence in the data, in the patterns, in the light itself. Sometimes astronomers talk about expansion as if it were a mathematical abstraction, a number in an equation, a slope on a graph. But if you think about it quietly, without equations, it's something far more poetic in its simplicity. The universe is not fixed, it's alive in a physical sense, dynamic, restless, always unfolding, and we are inside that unfolding, not outside looking in. Every atom of your body is carried along with that motion. You're part of a universe that refuses to stay still. It's humbling to think that what we call the night sky is really a time machine. The stars you see are ancient, and the space between them is stretching even as you look. The galaxies whose light reaches us tonight might never be visible again in the far future. Their light too stretched, their distance too great. Yet in this moment, they fill our sky with quiet testimony, evidence that the universe moves, grows, and changes. So when you look up again, maybe not tonight but some other night, remember that you're not looking at a static picture. You're looking at a living universe, one that's constantly in motion. Every photon, every flicker of starlight is part of an ongoing expansion that began long before you existed and will continue long after you're gone. It's not a distant process separate from you. It's happening everywhere, all the time, even now. And as we drift onward, carried by that same expanding space, our understanding keeps expanding with it. Each observation, each faint spectrum, each measurement adds a little more detail to the cosmic map. And with that growing picture comes another question, one that's been whispering in the background of everything we've discussed. What started the expansion in the first place? What caused the universe to begin stretching? And what traces of that moment still echo in the light we see today? Those echoes, it turns out, are all around us. They fill every corner of space, faint and cold but still detectable. The lingering warmth of creation itself. If you've ever wondered what the beginning of the universe might sound like if you could somehow hear it, that faint cosmic background is as close as you can get. It's the afterglow of the first moments still reaching us from a time when everything we now know was compressed into a single radiant fog. The night sky might seem like a picture of the present, but what you're really seeing is history stretched across space. Every star, every galaxy, every faint shimmer of light has been travelling toward you for ages. Some of that light began its journey long before Earth even formed, before the sun ignited, before there were oceans or clouds, or the idea of time measured in human hearts. And hidden within that ancient light, faint and cold, are the earliest whispers of the universe's birth, the echoes from the beginning. For a long time, astronomers believed that the stars had always existed. Even after the discovery that the universe was expanding, the idea of a clear beginning was difficult to grasp. If galaxies were moving apart now, it followed that they were once closer together. But how close? How far back could that expansion be traced? Was there truly a moment when everything, matter, energy, space, even time, began? The story of how we came to answer that begins with the simplest of clues: faint radio waves coming from every direction in the sky. The discovery was, as so many great discoveries are, accidental. In 1965, two radio engineers named Arno Penzias and Robert Wilson were working at Bell Laboratories in New Jersey. They were trying to build a sensitive antenna for satellite communications, a large, horn-shaped instrument capable of picking up extremely faint signals. But no matter how carefully they calibrated their equipment, they kept finding a strange background noise. It was constant, uniform, and came from everywhere at once. At first, they thought it might be interference. They checked the electronics, tightened the cables, and even cleared out nesting pigeons that had left a layer of debris inside the antenna. But nothing changed. The hiss remained, steady and unrelenting. Eventually, after consulting with a group of physicists working just down the road at Princeton, they realized what they had found was not noise from their equipment. It was the afterglow of the Big Bang, the lingering radiation from the moment the universe became transparent to light. That faint signal, now called the cosmic microwave background, is the oldest light we can see. It's the remnant of an era when the entire universe was filled with a hot, dense plasma of particles and radiation. In those early moments, light couldn't travel freely because it constantly scattered off electrons and protons. The universe was opaque, like a glowing fog. But about 380,000 years after the Big Bang, the temperature dropped enough for electrons and protons to combine into neutral atoms. Suddenly, light could move unimpeded. That light, the first light to travel freely through space, has been journeying ever since, stretched and cooled by the expansion of the universe, until it now appears to us as a faint microwave glow, just a few degrees above absolute zero. When Penzias and Wilson detected that signal, they were hearing the echo of creation itself, though they might not have thought of it that way at first. It was the confirmation of a prediction made years earlier by scientists who had proposed the idea of a hot, dense beginning. If the universe started in such a state, it should still be filled with residual radiation. The discovery of that background glow was the final piece of evidence that the Big Bang wasn't just a theory. It was the real story of how everything began. If you could somehow tune your radio to the right frequency, you could hear a trace of that ancient light even now. A small fraction of the static between stations comes from the cosmic microwave background. Every television screen, back when static-filled channels existed, contained a sprinkle of it too. Photons born in the universe's first moments, still arriving after more than 13 billion years. It's astonishing to think that the same light that once filled the entire cosmos now hums faintly in the background of our everyday technology. But the cosmic microwave background isn't just a relic, it's a message. Hidden within that glow are subtle variations, tiny fluctuations in temperature and density that mark the seeds of everything we see today. Those faint irregularities are what allowed gravity to begin gathering matter together, forming the first stars, galaxies, and clusters. Without them, the universe would have remained smooth and featureless, a uniform sea of energy. Instead, those minuscule ripples became the framework for all structure in the cosmos. When scientists mapped those variations in detail using satellites like COBE in the 1990s, then WMAP in the 2000s, and later the Planck spacecraft, they found a pattern so precise that it could tell them nearly everything about the universe's early conditions. The temperature of the background, the density of matter, the ratio of ordinary matter to dark matter, even the geometry of space itself, all of it was encoded in that faint radiation. It was as if the universe had left behind a baby picture of itself, a snapshot of what it looked like when it was only 380,000 years old. That snapshot told us something extraordinary. the universe was astonishingly uniform, but not perfectly so. The temperature variations across the entire sky are only about 1 part in 100,000. Those tiny differences might seem insignificant, but they are the fingerprints of the earliest quantum fluctuations, minute variations in energy that were stretched to cosmic scales during a brief but dramatic event called inflation. Inflation is one of the most fascinating ideas in cosmology. It proposes that in the first fraction of a second after the Big Bang, the universe expanded exponentially, faster than the speed of light, not because anything moved through space that quickly, but because space itself was ballooning. In that brief instant, a region smaller than an atom grew to the size of a galaxy and beyond. This sudden expansion smoothed out the universe, explaining why the cosmic microwave background looks so uniform in every direction. It also magnified tiny quantum irregularities into macroscopic ripples, which later grew into galaxies and clusters. Inflation turned microscopic randomness into cosmic structure. The evidence for inflation is indirect, but compelling. The uniformity of the cosmic background, the flatness of space, and the distribution of galaxies all point toward it. Yet, the exact mechanism remains mysterious. What caused inflation to start? What made it stop? These are questions physicists are still trying to answer. Some theories suggest that inflation was driven by a field of energy that temporarily dominated the universe, then decayed, releasing matter and radiation. Others propose that inflation might happen repeatedly in different regions, giving rise to multiple universes, a vast cosmic foam where each bubble has its own version of physics. Whether that's true or not, inflation helps explain why the universe we see today looks the way it does. Vast, smooth, and remarkably consistent. As expansion continued and the universe cooled, matter began to take shape. The first atoms formed, mostly hydrogen and helium, along with trace amounts of lithium. Gravity slowly began pulling those atoms together, forming the first clouds of gas. Within a few 100 million years, those clouds collapsed under their own weight, igniting the first stars. Those stars, enormous and short-lived, were unlike the ones we see today. They burned hot and bright, fusing hydrogen into heavier elements, and when they died, they exploded in brilliant supernovae, spreading those elements into space. From their ashes came new generations of stars, each one richer in the elements needed for planets, oceans, and life. In this way, the echoes from the beginning continued to shape everything that followed. The same radiation that Penzias and Wilson stumbled upon carries within it the memory of those early processes. When scientists analyze the spectrum of the cosmic microwave background, they can measure how much ordinary matter and dark matter existed, how fast the universe was expanding, and how that expansion has changed over time. It's as if the universe itself has been keeping a detailed record of its own growth, and all we have to do is learn how to read it. When you think about it, the idea that we can detect light from nearly 14 billion years ago is staggering. The photons that make up the cosmic microwave background have been travelling since the universe was young, and in all that time they've barely interacted with anything. They've crossed billions of light years, passing through expanding space, dodging galaxies, drifting endlessly until they finally arrive at detectors here on Earth. Every one of those photons is a messenger from the dawn of time. They carry the story of what the universe once was, and by extension, the story of everything that has happened since. That's why cosmologists often call the cosmic microwave background a window into the early universe. By studying it, they can infer what conditions were like long before the first galaxies formed. It's not just about understanding the past, it's about understanding the forces that still shape the cosmos today. The same expansion that stretched those photons is still at work, and by comparing how that expansion has changed over billions of years, scientists can begin to predict what might happen in the future. One of the most remarkable things about the cosmic background is how perfectly it fits with the idea of an expanding universe. As space stretches, the wavelength of the radiation stretches too. What began as visible or infrared light from the early universe has been stretched so much that it's now in the microwave range. That stretching is a direct consequence of expansion. The longer the light travels, the more it's stretched. The cosmic background is, in a sense, the universe's own evidence for its growth. It's the ongoing proof that space itself has been expanding for nearly 14 billion years. If you could somehow see the universe as it was then, it wouldn't look like the star-filled sky we see now. It would be an ocean of light, a blinding glow filling every direction, with no stars or galaxies, only a dense mist of plasma. Over time, as expansion continued, that glow dimmed and cooled, fading into the background we now detect only with specialized instruments. But that ancient light still surrounds us. Every cubic meter of space contains hundreds of those primordial photons, softly drifting through the cosmos. They're invisible to our eyes, but not gone. They're the lingering warmth of creation, the universe's faint afterimage of its own beginning. There's something strangely comforting about that. It means the traces of the earliest universe are still here, woven into the space between stars, between galaxies, between us. When you look at the night sky, you're not just seeing starlight from across the ages. You're also surrounded by the oldest light there is, a cosmic whisper that fills all of space equally, humming gently in the background of everything. It's not bright or loud, but it's constant, patient, and universal. When cosmologists map that radiation, they often render it as a colourful image. Red, blue, and yellow patches showing tiny temperature variations across the sky. But those colours are just a translation. In reality, the differences are minor, just millionths of a degree. Yet those tiny differences determined the entire future of the universe. Where the radiation was slightly denser, matter collected and galaxies formed. Where it was slightly thinner, vast voids expanded. From those microscopic ripples came all the complexity we now see. Stars, planets, people, everything. So when we talk about echoes from the beginning, we're not speaking metaphorically. Those echoes are real, measurable, and still arriving every second. They remind us that the universe isn't just a place of immense scale, but also of immense memory. It remembers its own birth, not in words or records, but in radiation, in patterns of light that stretch across the cosmos. Every telescope that measures that background is listening to those echoes, decoding the story written in photons, and that story is still unfolding. The universe continues to expand, the cosmic background continues to cool, and new generations of stars continue to form from the material forged in the first. The afterglow of the Big Bang connects us to that beginning, bridging billions of years of cosmic evolution. We live in a universe that carries its past with it, not as history, but as presence. The light of the beginning is still here, all around us, quietly telling the story of how everything began. As expansion continues and the cosmos grows colder and darker, that light will stretch even further. One day, trillions of years from now, it may be so faint that it becomes undetectable, but even then, it will exist, the final trace of the universe's first breath, the echo of a moment that set everything in motion. And as we continue our quiet journey through that expanding space, it's worth remembering that these echoes aren't just out there, they're also within us. The atoms in your body were forged in stars that formed from the gas left behind by the Big Bang. Every breath you take is filled with molecules whose origins trace back to that first moment. You are, in the most literal sense, made from the echoes of the beginning. Somewhere in the faint hum of that ancient radiation is the memory of everything that was, everything that is, and everything that will be. And as we follow those echoes forward, tracing them through time and distance, they lead us deeper into the question that has shaped all of cosmology. What is driving this expansion, and why does it continue to accelerate when it should be slowing down? When scientists first measured the expansion of the universe, they expected to find that it was slowing down. That seemed only logical. After all, everything that has mass exerts gravity, and gravity pulls things together. The more matter there is in the universe, the stronger that pull should be. Over billions of years, it was reasonable to think that the expansion left over from the Big Bang would gradually decelerate, tugged back by the collective weight of galaxies, stars, and dark matter. The question wasn't whether expansion would slow, but by how much, and whether gravity might eventually halt it altogether. For most of the 20th century, that was the general picture. The universe had been expanding since the beginning, but its future seemed destined for a long, slow settling. Then, in the 1990s, something unexpected happened. Something that would quietly overturn nearly a century of cosmic assumptions. Astronomers discovered that the universe wasn't slowing down at all. It was speeding up. The discovery came from a patient, meticulous effort to measure distances to faraway galaxies using one of the most reliable beacons in the cosmos, supernovae. These are exploding stars, brilliant enough to outshine entire galaxies for a short time. Among them, a particular kind, known as type Ia supernovae, burns with a predictable brightness. Because they all explode with nearly the same intrinsic luminosity, they serve as standard candles. By comparing how bright they appear from Earth to how bright they truly are, astronomers can calculate how far away they are. Two research teams, one led by Saul Perlmutter in California, and another led by Brian Schmidt and Adam Rees in Australia and the United States, set out to use these explosions to measure how the expansion rate of the universe was changing over time. They expected to find evidence of deceleration, the slowing effect of gravity. Instead, the data told a different story. Distant supernovae were dimmer than they should have been, as if they were farther away than predicted. That meant the universe had expanded more than anyone expected. At first, the results were met with disbelief. The idea that expansion could accelerate was almost unthinkable. It implied that some mysterious force was counteracting gravity on the larger scales, not just balancing it, but overwhelming it. As more data came in, however, the pattern became undeniable. The universe's expansion was indeed accelerating, and whatever was driving that acceleration seemed to be woven into the very fabric of space. Astronomers called this unknown influence dark energy. The name doesn't describe what it is, it simply acknowledges that it's energy, and that we can't see it. Dark energy isn't like the energy we're familiar with. It doesn't shine, it doesn't interact with light, and it doesn't clump together like matter. Instead, it appears to act as a property of space itself, an intrinsic pressure that causes space to stretch. The more space there is, the more dark energy there seems to be, and the faster expansion proceeds. It's a feedback loop written into the structure of the universe. To understand how something like this could exist, we have to look back to Einstein's equations of general relativity. When Einstein first formulated them, they described a dynamic universe, one that could expand or contract depending on its contents. But like many scientists of his era, Einstein assumed the cosmos must be static. To force his equations to yield that outcome, he introduced an extra term, the cosmological constant, represented by the Greek letter lambda. This term acted as a repulsive force that balanced gravity's attraction, holding the universe in equilibrium. Later, when Hubble's discovery revealed that the universe was expanding, Einstein famously abandoned the constant, calling it his greatest blunder. Decades later, the accelerating universe gave the cosmological constant a new life. What had once been a mathematical fix became a physical reality. Dark energy could be explained as a modern version of that same constant, a built-in energy density of space that doesn't dilute as the universe expands. Unlike matter, which becomes more sparse as space grows, dark energy remains constant in density, meaning that as more space is created, the total amount of dark energy increases. That's why its influence grows stronger over time, pushing the universe to expand faster and faster. But even this explanation leaves many questions unanswered. What exactly is dark energy made of? Is it truly constant, or does it change over time? Could it be something entirely different? A new field, a hidden property of the universe we've yet to discover? Observations so far suggest that dark energy behaves like the cosmological constant, but the data aren't precise enough to rule out other possibilities. Some theories propose that it might be linked to quantum fluctuations of the vacuum, the background energy that exists even in empty space. Others suggest it could be a dynamic field, one that evolves as the universe expands. Whatever it is, dark energy dominates the cosmos. About 70% of the total energy content of the universe is attributed to it. Dark matter makes up another 25%, and the ordinary matter, everything we can see, touch, and measure directly, accounts for less than 5%. In other words, most of the universe is made of things we don't understand. What we call reality, the visible universe, is just a thin layer floating on top of a vast ocean of the unknown. To picture how dark energy works, imagine two galaxies separated by vast stretches of space. Gravity tries to pull them together, but dark energy pushes the space between them to expand. At first, gravity might have the upper hand, slowing the expansion, but as the galaxies drift apart, the influence of dark energy increases. Eventually it overcomes gravity's pull, and the galaxies begin to recede from each other faster than ever. The more space between them, the stronger dark energy's effect becomes. It's a slow but relentless process, one that defines the universe's current era. This acceleration has measurable consequences. It affects how galaxies cluster, how light bends as it passes through space, and how the cosmic microwave background appears to us. By studying these effects, astronomers can infer how dark energy behaves. Large surveys, like those conducted by the Sloan Digital Sky Survey and the Dark Energy Survey, have mapped millions of galaxies to trace the cosmic web and see how it changes over time. Each data point helps refine our understanding of the universe's expansion history and its possible futures. Still, dark energy remains one of the most elusive concepts in all of physics. It doesn't behave like anything else we know. It doesn't interact with matter except through gravity. It doesn't form structures or emit radiation. It's invisible, yet it shapes the fate of everything. Some scientists have even suggested that our understanding of gravity itself might need revision, that perhaps what we call dark energy is a sign that general relativity, brilliant as it is, might be incomplete on cosmic scales. But for now, the simplest explanation remains that dark energy is real, uniform, and accelerating the universe's expansion. The discovery of dark energy also reshaped how we think about the ultimate fate of the cosmos. In a universe without it, gravity would eventually slow expansion and perhaps reverse it, leading to a collapse, a big crunch. But with dark energy driving acceleration, such an ending seems less likely. Instead, the universe may continue expanding forever, growing colder and more diffuse with each passing epoch. Galaxies will drift beyond each other's horizons, their light fading until the sky grows empty. Stars will burn out, black holes will evaporate, and the universe will approach a quiet, frozen state, a big freeze. That vision might sound bleak, but it's not without a certain serenity. A cosmos that fades gently into stillness is a universe that has fulfilled its evolution. It's a vast natural process, unfolding without violence or sudden end, and yet, even that scenario depends on what dark energy truly is. If it changes over time, if its strength increases, then the expansion could become catastrophic. Galaxies, stars, planets, even atoms could eventually be torn apart in what physicists call the Big Rip. That possibility remains speculative, but it's a reminder of how much we still don't know. The fate of everything depends on the properties of something we can't yet see or touch. To understand just how mysterious dark energy is, consider that its density is incredibly small. A single cubic meter of space contains less than a 10 billionth of a joule of dark energy, the energy equivalent of a mosquito's movement. Yet because the universe is so vast, the total amount adds up to dominate its entire evolution. It's the perfect example of how the cosmos operates on scales that defy intuition. The faintest force acting over the greatest distances can outweigh everything else. Some experiments are trying to detect dark energy's effects more directly. Space missions like the upcoming Euclid telescope and the Vera Rubin Observatory aim to measure the distribution of galaxies and the bending of light caused by massive structures, refining our estimates of how expansion changes over time. These observations might reveal whether dark energy is constant or dynamic. On a more theoretical front, physicists are exploring whether dark energy might arise from the energy of the quantum vacuum. The idea that even empty space teems with fluctuations of virtual particles appearing and disappearing. If that's true, then dark energy could be a natural consequence of quantum physics. The problem is that when we try to calculate the vacuum energy using known physics, the result is off, not by a small margin, but by a factor of about 10 to the power of 120. It's the largest discrepancy between theory and observation in all of science. That mismatch tells us something profound. Either our understanding of quantum physics is incomplete, or our interpretation of how vacuum energy interacts with gravity is wrong. In either case, dark energy sits at the intersection of our greatest theories, general relativity and quantum mechanics, and exposes the limits of both. It's as if the universe has presented us with a riddle, one that can't be solved without rewriting the laws of nature themselves. Even so, there's something strangely fitting about that. The cosmos has always kept some of its workings hidden, revealing just enough to pull us forward. Dark energy is part of that hidden order, an invisible hand guiding the expansion, shaping the large-scale structure of everything we can see. It's not malicious or benevolent. It simply is. It's the quiet force that ensures the universe will never stop growing. When you think about the word dark, it's easy to imagine something ominous. But in science, dark simply means unseen. Dark matter, dark energy. They're not dark in the sense of absence, but in the sense of mystery. They're parts of the universe that haven't yet come into the light of understanding. And perhaps that's what makes studying them so captivating. Every measurement, every faint observation, brings us a little closer to seeing what was once invisible. Right now, as you listen, space itself is expanding faster than it was when this sentence began. Not by much, not enough to measure directly, but enough that over billions of years the difference becomes immense. Every distant galaxy is being carried away by that acceleration. The light they emit stretches as it travels, red-shifting more and more until eventually it will slip beyond the range of detection. The night sky will grow emptier, quieter, darker. The universe will keep expanding, and dark energy will keep working, silently, invisibly, everywhere. It's strange to think that the same physical laws that govern your heartbeat and the motion of atoms also govern this cosmic acceleration. The same equations describe both, scaled across unimaginable distances. You are, in a sense, part of that expansion. The atoms in your body are separated by forces that resist the cosmic stretching, but the space between galaxies, as between clusters, between the great filaments of the universe, continues to grow. You're made of matter that tries to hold itself together while the universe around you drifts apart. And yet, despite all this motion, there's an order to it. Dark energy doesn't create chaos. It creates structure through its balance with gravity. Without it, the universe might have collapsed long ago. With too much of it, the cosmos might have torn itself apart before galaxies could form. Somehow it seems to exist in just the right proportion to allow everything we know to exist. A balance so delicate that even a tiny change could have produced a completely different universe. That's one of the most remarkable things about cosmology. The constants of nature, the values that define how strong gravity is, how fast light travels, how much energy space contains. They all seem fine-tuned to allow complexity, life, and consciousness to arise. Some see that as coincidence, others as inevitability, and still others as evidence of deeper principles we don't yet understand. Whatever the explanation, it makes the universe feel less like a random accident and more like an intricate system still revealing its design. When astronomers look into the deep sky and measure distant galaxies, they're not just collecting data, they're watching dark energy at work. Each faint smear of light is a piece of the puzzle, a record of how the universe has been expanding over time. The farther they look, the further back in time they see, and the more they learn about how dark energy's influence has evolved. The sky, in this sense, is a living archive of cosmic acceleration. It's worth pausing to reflect on what that means. We live in a universe driven by something we can't see, governed by laws we only partly understand, and yet, from our small corner of space, we can measure its expansion with astonishing precision. We can trace the faintest signals across billions of years and use them to piece together the story of everything. The fact that we can do that conscious beings, made from stardust and bound by gravity, can comprehend the acceleration of the entire cosmos, is perhaps the most extraordinary mystery of all. And so, as the universe continues to expand, carried by this invisible hand, the questions remain. What is dark energy? Why does it exist? Is it constant, or will it change, rewriting the fate of the cosmos? For now, all we can do is observe, measure, and wonder. The answers may come slowly, perhaps over generations, but the pursuit itself, the act of listening to the universe, of following its expansion to its source, is part of what makes us human. Somewhere beyond the light of the nearest stars, beyond the reach of any telescope, dark energy continues its quiet work, pushing galaxies apart, stretching space itself, ensuring that the story of the universe will go on. And as it does, we keep following the traces it leaves behind, the faint signals, the subtle shifts, the whispers of acceleration written across the sky. If the universe could speak, its language would be the balance between two simple ideas, the pull of gravity and the push of expansion. Everything that has ever happened, from the birth of stars to the stretching of galaxies, is shaped by those opposing forces. They don't compete in the way we think of a struggle, but rather exist in a kind of quiet negotiation. One pulls, one pushes, and between them lies the story of everything. Gravity is familiar. It's what keeps your feet on the ground, what holds the moon in orbit around the Earth, what binds planets to the sun and stars into galaxies. It's the oldest known force, the one that gave shape to the universe long before we had words for it. But gravity is also subtle. It's the weakest of the fundamental forces, yet because it only pulls and never cancels itself out, its effects add up across vast distances. The combined gravity of billions of stars can hold a galaxy together. The combined gravity of billions of galaxies can shape the entire cosmic web. The other force, if we can even call it that, is newer to our understanding. Expansion isn't a traditional force in the sense of a push from one object to another. It's an intrinsic property of space itself. It's not something acting within the universe. It's something the universe does. When cosmologists talk about the expansion of space, they don't mean galaxies flying apart through emptiness. They mean that the emptiness itself is stretching, carrying everything with it. That expansion is driven, as far as we can tell, by dark energy, the mysterious pressure woven into the fabric of space. The balance between these two influences has shaped the universe from its earliest moments. In the beginning, after the Big Bang, expansion was dominant. Space itself was growing at an incredible rate, faster than the speed of light. Then, as the universe cooled and matter formed, gravity began to take hold. Over billions of years, it gathered gas into stars, stars into galaxies and galaxies into clusters. For a time, gravity seemed to have the upper hand. The expansion slowed, though never stopped. Then, a few billion years ago, something shifted. Dark energy began to dominate, and expansion started to accelerate once again. This alternating balance, first expansion, then gravity, then expansion again, defines the large-scale evolution of the cosmos. It's as though the universe has tides, rising and falling across epochs measured not in years but in billions of years. And right now, we're living in the era when dark energy's tide has risen, pushing everything apart faster than before. To imagine how these two influences interact, think of the universe as a vast ocean. Gravity is the current that pulls matter together into eddies and whirlpools. Galaxies, clusters, stars. Expansion is the tide that stretches the surface, slowly drawing those whirlpools farther apart. The galaxies themselves aren't growing larger, the space between them is. On small scales, gravity dominates, binding things tightly. On cosmic scales, expansion takes over, carrying entire clusters away from each other. The line between those two regimes, where gravity stops winning and expansion starts, depends on scale and time. In the early universe, matter was dense and gravity reigned. The galaxies were close together, and their mutual attraction slowed expansion slightly. But as space continued to stretch, the density of matter decreased, and dark energy, whose density stays roughly constant, began to dominate. It's a slow transformation, but one with profound consequences. The more the universe expands, the more dominant dark energy becomes. Eventually, if current models are correct, gravity will only matter within local islands of matter, galaxies and clusters, while the vast spaces between them will drift beyond reach. You can already see this process in the night sky. The Milky Way, along with the Andromeda Galaxy and a few dozen smaller companions, are bound together by gravity in what we call the local group. These galaxies are close enough that gravity overcomes expansion. In about 4 billion years, the Milky Way and Andromeda will merge into a single, larger galaxy. Beyond that, though, the nearby Virgo cluster and all other large structures are moving away, carried by the expansion of space. Over tens of billions of years, they'll recede so far that their light will no longer reach us. Gravity keeps our local corner of the universe together, but expansion ensures that beyond a certain horizon, everything slips away. The cosmic tug-of-war between gravity and expansion isn't just theoretical. It's visible in the structure of the universe itself. When astronomers map the distribution of galaxies on enormous scales, they see a delicate pattern, a vast network of filaments and voids. The filaments are regions where matter has clumped together under gravity. The voids are regions where expansion has stretched space faster than matter can collect. It's a balance written across billions of light years, a record of how those two forces have interacted since the beginning. This balance also defines time in a cosmic sense. Gravity slows time slightly in regions of strong curvature, near massive objects. Expansion, on the other hand, defines the large-scale flow of time across the universe. As space expands, the wavelengths of light stretch, and so does time itself. When we observe distant galaxies, their light not only arrives red-shifted, the events we see unfold more slowly, stretched by the expansion. Time, like space, is part of that same fabric. The push and pull of gravity and expansion shape not just where things are, but when they are. In the early universe, gravity works tirelessly to gather matter into structures. The competition between attraction and expansion determined which regions would form galaxies and which would become empty space. Where matter was slightly denser, gravity gained a foothold. Those regions grew, pulling in more material until stars began to ignite. Where matter was less dense, expansion won, leaving behind cosmic voids. Over billions of years, this interplay sculpted the universe's architecture. What's striking is how delicate this balance is. If gravity had been just a little stronger relative to expansion, The universe might have collapsed back into itself long ago. If expansion had been slightly stronger, matter might have dispersed too quickly for galaxies or stars to form. The fact that we exist at all, in a universe stable enough for complex structures, depends on that balance being just right. Cosmologists often refer to this as fine-tuning, the idea that certain parameters of the universe must fall within narrow ranges for life and structure to be possible. Whether that fine-tuning is coincidence, necessity, or evidence of something deeper remains one of the great open questions. Even now, that balance plays out in quiet ways. Every time a star forms, gravity is momentarily victorious. Gas clouds collapse under their own weight, igniting nuclear fusion. But eventually even stars lose to expansion. Their light spreads outward, red-shifted by the stretching of space, until it fades into the background. On cosmic scales, expansion always has the final say. Gravity creates islands of order, but expansion defines the ocean they float in. There's a kind of melancholy beauty in that idea, that every galaxy, every star, every moment of structure exists because gravity resists the inevitable stretching, yet cannot stop it forever. Over time, gravity's domain shrinks. The cosmic horizon grows. More of the universe becomes unreachable, hidden beyond the limits of light. In the far future, even if stars still burn in some distant cluster, they will do so in an increasingly empty sky, each one isolated by the vastness of expanding space. Still, for now, the balance holds. Within galaxies, gravity is strong enough to maintain order. Stars orbit their centers, planets circle their stars, and life emerges in small, stable pockets. Expansion only becomes noticeable when we look far beyond, when we measure light from distant galaxies and see how it's been stretched. That's the scale on which dark energy and gravity perform their slow dance. Understanding this balance requires both theory and observation. On the theoretical side, general relativity provides the framework. Einstein's equations describe how matter tells space how to curve, and how space tells matter how to move. Expansion emerges naturally from that geometry. Gravity curves space inward, while dark energy curves it outward. The overall curvature of the universe, whether it's open, closed, or flat, depends on which influence dominates. Observations of the cosmic microwave background suggest that the universe is remarkably flat, meaning that gravity and expansion are almost perfectly balanced on the larger scales. That balance isn't static, though. As the universe expands and matter becomes more diluted, the influence of dark energy grows. On the observational side, astronomers measure the balance through redshift surveys, galaxy clustering, and the behavior of large-scale structures. When they map the distances to thousands of galaxies, they can see how expansion affects their distribution. They can also observe how gravity has pulled matter into clusters and how dark energy has stretched the space between them. These measurements, taken together, allow scientists to reconstruct the universe's expansion history. It's a kind of cosmic archaeology, uncovering the layers of motion that have built the present. What emerges from these studies is a picture of a universe in dynamic equilibrium. Not static, not chaotic, but governed by simple relationships that play out over unimaginable timescales. Gravity and expansion aren't enemies, they're partners in creation. Gravity gathers, expansion disperses. Together they produce the diversity and structure we see. Without gravity there would be no stars, no planets, no life. Without expansion, everything would have collapsed before it could begin. You can feel that balance reflected in smaller ways too. Gravity binds your body to the earth, keeps the oceans in rhythm with the moon, shapes the motion of everything familiar. Expansion, though imperceptible on those scales, is the quiet backdrop, the context in which all that binding takes place. You are, right now, sitting in the middle of both influences, held by one and carried by the other. In cosmological terms, the current era is something of a transition. We live at a time when both gravity and expansion are still significant. Galaxies continue to form, Stars continue to shine, and yet the acceleration driven by dark energy has already begun to change the large-scale landscape. In the distant future, that balance will shift more dramatically. Expansion will accelerate to the point where distant galaxies move away faster than light, disappearing beyond the cosmic horizon. Gravity will still hold local systems together, but the universe as a whole will grow increasingly empty. It's a strange thing to contemplate. A universe that was once dense and fiery becoming cold and diffuse, all because of the quiet interplay between two forces. But it's also a reminder of how everything in nature depends on contrast. There's no expansion without gravity to measure it against, no structure without something to resist. Even in the cosmos, creation is balance. Astronomers sometimes refer to this relationship as the cosmic tug-of-war, but it's less of a battle and more of a partnership. Each side defines the other. Gravity gives shape, expansion gives direction. Without expansion, the universe would have no scale. Without gravity, it would have no form. The two together create a kind of harmony, a balance that allows both change and stability. When you look up at the stars, you're seeing that harmony in action. Every point of light represents a victory for gravity, a region where matter has come together against expansion's pull. Every patch of darkness between them represents expansion's triumph. Space stretched too thin for new stars to form. Together, they paint the universe in a pattern of light and dark, attraction and dispersal, creation and release. That pattern isn't static. It's changing even now, subtly and silently as expansion continues. The galaxies that make up our visible universe today are only a small part of what exists. Beyond them lie countless others, receding faster than light can carry their signal to us. We'll never see them, but they're there, following the same laws, caught in the same balance. And as the centuries pass, the view from any given point in space will change, the visible horizon shrinking as expansion accelerates. In the end, gravity and expansion are two expressions of the same thing, the geometry of space-time. They aren't separate forces so much as two aspects of how energy and space interact. One draws matter inward, the other stretches it outward, and together they define the rhythm of cosmic evolution. It's that rhythm that gives rise to everything: galaxies, clusters, filaments, voids, and the vast expanding universe itself. And as we continue to follow that rhythm forward, we begin to approach the next question. Not just how these forces shape the universe now, but how we measure their work. How do we know how fast the universe is expanding? How do we measure something so vast, so subtle, that it changes by imperceptible amounts over millions of years? When you hear that the universe is expanding, it sounds almost straightforward. Space is growing, galaxies are moving apart, and the distances between them increase over time. But behind that simple description lies a challenge that has occupied astronomers for nearly a century. How do you measure something that vast, that subtle, that slow? How do you measure forever? The expansion of the universe isn't something that can be seen directly, not in the way you might measure the growth of a tree or the flow of a river. It's a change in the distances between galaxies that unfolds over billions of years. No telescope can watch it happen in real time. Instead, scientists infer expansion from light, from how it travels and changes as it crosses space. The key is redshift, that gentle stretching of light waves as they move through expanding space. The farther a galaxy is, the more its light has been redshifted. By measuring that shift and comparing it with the galaxy's distance, astronomers can calculate the rate at which the universe expands. That rate has a name, the Hubble constant. It's one of the most important numbers in cosmology, and one of the most debated. The Hubble constant tells us how fast the universe is expanding at the present time, typically expressed in kilometers per second per megaparsec. That means that for every million parsecs, roughly 3.26 million light-years, of distance, galaxies move away from us a certain number of kilometers per second due to the expansion of space. It's not just a number, it's a key that unlocks the age, size, and future of the cosmos. The history of measuring that number is a story of ingenuity, patience, and sometimes frustration. It began, fittingly, with Edwin Hubble himself in the 1920s. Using the Hooker telescope at Mount Wilson, he compared the distances to nearby galaxies with their redshifts, measured earlier by Vesto Slipher. The result was a roughly linear relationship. The farther away a galaxy was, the faster it appeared to be receding. Hubble plotted the data and found a slope. That slope became the first estimate of the Hubble constant. His original value, about 500 kilometers per second per megaparsec, was wildly off due to calibration errors, but the concept was revolutionary. It showed that the universe was not static, but expanding. Since then, the effort to measure the Hubble constant accurately has been a kind of cosmic detective story. Each generation of astronomers has refined the tools, the data, and the techniques, trying to pin down a number that defines the tempo of the entire universe. The problem is that measuring distances in space isn't simple. You can't stretch a ruler between galaxies. Every measurement depends on a chain of assumptions, each link built from the one before it, a series of cosmic yardsticks known collectively as the distance ladder. At the base of that ladder are objects whose distances can be measured directly, usually within our own galaxy. Parallax, the slight shift in a star's apparent position as Earth orbits the Sun, provides the first step. It's geometry, pure and simple, the same principle surveyors use to measure distances on Earth. From that, astronomers calibrate the brightness of certain types of stars like Cepheid variables. These stars pulse with a regular rhythm, and the period of their pulsation is directly related to their intrinsic brightness. By comparing their true brightness with how bright they appear, you can determine how far away they are. Cepheids become the next rung on the ladder. Beyond Cepheids come Type Ia supernovae, the bright, predictable explosions of dying stars. They all reach nearly the same peak luminosity, making them excellent standard candles for measuring distances to galaxies far beyond our own. By combining supernova observations with redshift data, astronomers can map how the expansion rate changes over billions of years. Each step up the ladder extends our reach, allowing us to measure farther into space and deeper into the past. The process sounds neat and linear, but in practice it's painstaking. Each link in the ladder introduces uncertainties, calibration errors, environmental effects, observational limitations. Over the years, as measurements became more precise, those uncertainties narrowed, but they never disappeared. And recently, a new and intriguing problem has emerged. Two independent methods of measuring the Hubble constant, both robust, both grounded in solid data, give slightly different answers. The discrepancy has become one of the most interesting puzzles in modern cosmology. One method uses the distance ladder described above, relying on Cepheids and supernovae to measure how fast nearby galaxies are receding. This approach, refined by the SUES project led by Adam Rees and his team, yields a value around 73 kilometers per second per megaparsec. The other method bypasses the local measurements entirely, using data from the cosmic microwave background, the faint afterglow of the Big Bang. By analysing patterns in that radiation, particularly the spacing of temperature fluctuations, cosmologists can infer how fast the universe must be expanding today. The Planck satellite, which mapped the cosmic microwave background in exquisite detail, gives a value closer to 67. The difference might not sound dramatic, but in science, a few kilometers per second per megaparsec translates into a deep question about how the universe works. The two values are far enough apart that they can't be explained by simple measurement errors. If both are correct within their margins of uncertainty, it means something fundamental might be missing from our understanding. This tension between measurements, often called the Hubble tension, could be a sign of new physics. Some scientists suggest that dark energy might not be constant after all. If its properties have changed over time, the expansion history of the universe might not match the assumptions built into our models. Others propose that there could be new types of particles or interactions we haven't yet discovered, something that subtly altered the early universe's behavior. Still others suspect that our understanding of cosmic inflation or dark matter might need revision. Whatever the explanation, it's clear that even a small disagreement in a single number can open vast doors of inquiry. It's remarkable how far we've come in measuring something so abstract. The tools now available are almost beyond imagination compared to Hubble's day. The Hubble Space Telescope itself, ironically named, became one of the key instruments for refining the Hubble constant, using its sharp resolution to observe Cepheids and supernovae in distant galaxies. Later, the Planck satellite and the Wilkinson microwave anisotropy probe mapped the cosmic microwave background with incredible precision, turning faint variations in ancient light into a detailed record of the universe's structure. Each of these missions added layers of clarity, yet also deepened the mystery of why the numbers don't quite agree. New techniques continue to emerge, offering independent ways to measure cosmic expansion. One involves gravitational lensing, where the gravity of massive galaxies bends and magnifies the light of objects behind them. By studying how the light from distant quasars or supernovae is delayed and distorted as it passes through these cosmic lenses, astronomers can infer the universe's expansion rate without relying on the traditional distance ladder. Another technique uses gravitational waves, ripples in space-time created by colliding neutron stars or black holes. These events produce both light and gravitational signals, allowing scientists to compare their arrival times and estimate distances directly. Such standard sirens could one day provide a new rung on the cosmic ladder, independent of the others. Each of these methods approaches the same fundamental question from a different angle. How fast is space stretching right now? The answer determines not only the size of the observable universe, but also its age. A faster expansion means a younger universe, since it would have reached its current size more quickly. A slower expansion implies an older universe. Using current measurements, cosmologists estimate the universe's age to be about 13.8 billion years, but that number depends directly on the Hubble constant. If the tension between the different methods persists, even that age might need revisiting. There's a quiet elegance in how these measurements are made. Light, the most ephemeral thing, becomes a ruler that spans the cosmos. A photon leaving a distant galaxy carries with it the imprint of space's expansion, stretched over billions of years. By the time it reaches us, its wavelength has lengthened, its energy has diminished, and its colour has shifted toward red. That change encodes the entire history of the universe's growth along its path. Astronomers decode that signal with precision instruments, turning faint light into data, data into numbers, and numbers into insight. It's as if the universe keeps its own record of time in the light it sends across the void. What's perhaps most humbling is that this effort to measure forever rests on moments that are fleeting. A supernova burns for only weeks or months. A Cepheid star pulses over days. Yet by studying those brief flashes we measure billions of years. Human instruments, human lifetimes, capture these moments and use them to glimpse eternity. It's an extraordinary act of imagination and precision, built on patience and collective curiosity. There's a certain irony too in the fact that we can measure the expansion of the universe more precisely than we can explain why it's happening the way it does. We can describe the rate, chart its changes, and model its future, but the underlying cause, dark energy, remains mysterious. It's like knowing the beat of a drum perfectly while still not knowing who's playing. And yet, the act of measuring has value beyond the numbers. Each refinement tells us something about how the universe behaves. Even the disagreement between methods is informative. It shows us where our theories might be incomplete. In that sense, measurement is not just about finding answers, but about locating the edges of what we don't yet understand. The Hubble constant, in its elusive precision, becomes a kind of cosmic mirror. It reflects both our ability to observe and the limits of our knowledge. When you think about what it takes to measure expansion, it's hard not to feel a quiet awe. Every piece of data depends on light that has travelled unimaginable distances, crossing time itself to reach us. A photon captured by a telescope tonight may have left its source when the first multicellular life was forming on Earth, or before Earth even existed. And in that photon's wavelength lies a clue about how much space has expanded since it began its journey. That's what makes cosmology so profound. It turns the faintest signals into stories about the deepest truths. All these measurements point toward one conclusion. The universe is expanding, and it's doing so at an accelerating rate. The numbers may differ slightly, but the trend is undeniable. The space between galaxies grows. The light from distant objects stretches. Time itself, in a cosmic sense, moves to the rhythm of that expansion, and every effort to measure it, every observation, every refinement, is a step toward understanding not just how the universe behaves, but why it exists in this form at all. It's tempting to think of this work as abstract, distant, something for observatories and data models. But at its core, it's a deeply human endeavour. The same instinct that makes a child wonder how far away the stars are drives astronomers to measure the expansion of space. It's the continuation of a very old curiosity, a desire to know where we are, when we are, and what it all means. Measuring forever isn't just a scientific act, it's an expression of wonder. As you listen, somewhere in the darkness, another photon is beginning its long journey. It leaves a galaxy billions of light years away, carrying with it the faint signature of expansion. It will travel across the void for eons, stretched by the growth of space, before perhaps one day being caught by a telescope not yet built, on a planet not yet born. When that happens, it will tell the story of how the universe expanded, how fast and for how long. It's a story still being written, in light, in data, in time. When we picture the universe expanding, it's easy to imagine that it has always done so in the same way. Galaxies drifting steadily apart, space stretching evenly across time. But the reality is more complex. The rate of expansion has not been constant. It has changed, responding to the cosmic balance between matter, radiation, and that strange, elusive influence we now call dark energy. The universe has slowed, it has sped up, and through those changes it has revealed something profound about its own nature. If we could somehow watch the entire history of the universe unfold in a single, continuous view, from its fiery beginning to this quiet moment now, we would see expansion behaving almost like a living rhythm. It began with unimaginable speed, slowed as gravity took hold, and then, long after the first stars were born, began to accelerate again. Each phase tells a different story, shaped by the ingredients that dominated the cosmos at that time. In the earliest moments, everything was governed by radiation. The universe was hot, dense, and filled with energetic particles and light. Matter, as we know it, barely existed in any stable form. Photons and particles constantly collided, exchanging energy, keeping everything in equilibrium. In that era, expansion was driven by the tremendous energy of radiation itself. The more energy the universe contained, the faster it expanded. But as space stretched, that energy thinned out. Photons lost energy as their wavelengths lengthened, cooling the universe. As the radiation faded, matter began to dominate. At first, this matter was just hydrogen and helium gas, still too hot to clump together. Over time, gravity started to gather it into clouds, then stars, then galaxies. The pull of that gravity acted against the expansion. Each galaxy, each cluster, slowed the cosmic growth slightly, tugging inward on its neighbours. For billions of years, this struggle continued. The universe expanding from its initial momentum while gravity fought to hold it back. If the universe contained only matter and radiation, that tug of war would have continued indefinitely, with gravity gradually winning. The expansion would slow more and more, perhaps eventually halting, the fate of everything would depend on the total amount of matter in existence. Too little, and expansion would continue forever, though ever more slowly. Too much, and gravity would eventually reverse it, pulling everything back together in a colossal collapse, a big crunch. For most of the 20th century, astronomers debated which of these futures awaited the cosmos. They tried to measure the universe's density, searching for the critical threshold that would determine its fate. The term critical density became a kind of cosmic dividing line, the balance point between internal expansion and eventual collapse. If the average density of matter was greater than this critical value, the universe would be closed, destined to contract. If it was lower, the universe would be open, expanding forever. Measuring that value became one of the central goals of cosmology. The results were frustratingly inconclusive for decades. Some measurements suggested a dense universe, others a sparse one. But then, in the late 1990s, came the discovery that changed everything. The realization that expansion wasn't slowing at all. It was speeding up. The cosmos, once thought to be in a graceful deceleration under gravity's pull, was in fact racing outward faster than before. The driver of that acceleration was dark energy, an invisible pressure woven into space. That finding transformed the question entirely. The critical density still mattered, but now it included not just matter and radiation, but dark energy as well. The universe was not merely expanding under its own momentum, it was being actively pushed apart by something deeper, something that behaved as though empty space had energy built into it. And because dark energy doesn't thin out as the universe expands, unlike matter and radiation, which become more dilute, its influence grows stronger over time. That shift from slowing to speeding marked a turning point in cosmic history. It happened about 5 billion years ago, when the universe was roughly 2/3 its current age. Before that time, matter was still dense enough for gravity to slow expansion. After that point, as galaxies drifted farther apart and space grew more empty, dark energy took over. From then on, acceleration became the dominant trend. To understand what that means, imagine the universe as a car moving along a long, curving road. In its early years, the car was moving fast, fueled by the immense energy of the Big Bang. Then, as gravity began to assert itself, the car started to slow down, not stopping, but losing speed steadily. After billions of years, just when it seemed destined to coast forever, an unseen engine kicked in, pushing the car faster again, its acceleration increasing with every mile. That hidden engine is dark energy, and it's still running. The evidence for this change doesn't come from watching galaxies move. They're too distant and their motion too slow to see directly, but from the light they emit. By measuring the brightness and redshift of distant supernovae, astronomers can reconstruct how expansion has changed over time. Light from explosions billions of years ago shows that galaxies were closer together then than they would be if the expansion had always been constant. When those data are plotted, the curve isn't linear. It bends, first slowing, then steepening. That bend is the signature of acceleration, written in the light of dying stars. Other lines of evidence support the same picture. The cosmic microwave background, the afterglow of the Big Bang, shows tiny fluctuations that reveal the early expansion rate. By comparing that with the structure of galaxies today, scientists can see how expansion has evolved. The differences between the two eras, the early deceleration and the recent acceleration, match the predictions of a universe governed by dark energy. The data form a consistent narrative, one that traces the entire arc of cosmic expansion from its beginning to now. But beneath that elegant pattern lies a puzzle that still unsettles cosmologists. Why did dark energy begin to dominate when it did? There's nothing in the equations that explains the timing. For billions of years, its effects were negligible, hidden beneath the influence of matter. Then, seemingly without cause, it began to take over. The coincidence seems almost too perfect, as if the universe waited until galaxies and life had formed before changing its tempo. Some scientists call this the cosmic coincidence problem. Why now? Why us? There's no clear answer. It may be mere coincidence, or it may point to something deeper about the nature of dark energy itself. If you step back and look at the timeline, the pattern is astonishing. The first few moments of the universe were dominated by radiation. Then, for billions of years, matter ruled, shaping stars and galaxies under gravity's slow influence. And now, dark energy has become the master force. Each era tells the story of a different balance. Each change of dominance rewrites the universe's behaviour. The slowing of the past and the speeding of the present aren't just numbers, they're the fingerprints of those shifting cosmic rulers. Even though acceleration defines the universe now, gravity hasn't vanished. It still binds galaxies, still forms stars, still shapes the local universe. But on the grand scale, its influence grows weaker as matter becomes more diffuse. Expansion stretches the distances between clusters faster than gravity can bridge them. The cosmic web remains, but its filaments thin. In the far future, if dark energy continues to dominate, only local structures, galaxies and clusters bound by gravity, will remain connected. Beyond them, everything will drift into darkness, unreachable and unseen. There's a quiet irony in that. The same discovery that revealed the universe's acceleration also ensured that future observers, billions of years from now, might never see evidence of it. As expansion continues, distant galaxies will disappear beyond the cosmic horizon. The night sky will fade. The clues to the universe's past, the red shifts, the cosmic background radiation, even the faint glow of distant galaxies, will vanish. Future civilizations might once again believe the cosmos is static, unable to detect the expansion that defines it. We live at a moment when the evidence is still visible, when the universe's history is still legible in light. It's tempting to think of the universe's changing expansion as a kind of breathing, a long, slow inhale and exhale stretched across eternity. Expansion, gravity, acceleration, all parts of a rhythm too vast for us to hear directly. We see it only in traces, in the way light bends, in the way galaxies cluster, in the way distant supernovae fade. Each observation is a snapshot of the universe at a different beat of that rhythm. By assembling those snapshots, we can reconstruct the cosmic symphony, even if we can't hear it unfold in real time. But as precise as our instruments have become, there's still uncertainty. We know the universe is accelerating, but we don't know whether that acceleration will continue forever, whether it might change, or whether it could someday reverse. Our models describe what's happening now, not necessarily what will happen next. Dark energy's true nature could shift over time, leading to outcomes we can't yet predict. It might remain constant, producing eternal expansion. It might grow stronger, leading to a catastrophic tearing apart of everything. Or just possibly it might weaken, allowing gravity to regain control. The problem is that all of these futures look nearly identical today. The differences would only become apparent over billions of years. That's what makes cosmology both humbling and exhilarating. We can see far, but not far enough to know everything. The light that reaches us carries messages from the past, not from the future. We infer what comes next based on what has already been, but the universe is under no obligation to continue its story the same way. Even so, each new measurement sharpens our view. The Hubble tension, that small but persistent disagreement about the rate of expansion, might be a clue that dark energy isn't as simple as we think. It could be evolving, changing the tempo of the universe's acceleration in ways too subtle for us to detect yet. The next generation of telescopes, like the Euclid mission and the Vera Rubin Observatory, will map galaxies with unprecedented detail, measuring how expansion changes across space and time. Those observations might reveal whether the speeding continues steadily or shifts again. It's worth pausing to realise how extraordinary it is that we can even ask these questions. A few hundred years ago, humanity didn't know there were other galaxies. A century ago, we didn't know the universe was expanding. A few decades ago, we didn't know it was accelerating. And now, we're debating the nuances of that acceleration, whether it's constant, changing, or something entirely new. The progress is staggering, but it also reminds us how provisional every understanding is. The universe keeps deepening, just when we think we've grasped its scale. When you trace the story of expansion, the slowing, the speeding, the unknown, you see the universe not as a static thing, but as an evolving process. It changes, reacts, adjusts, following laws we can describe but not yet fully explain. In that sense, it's alive in a way, not conscious but dynamic, responsive. It's an unfolding of reality itself, guided by the simplest and most mysterious principles: gravity pulling in, expansion pushing out, and dark energy steering the balance between them. Right now, that balance leans toward expansion. The universe grows faster every moment, and the distances between galaxies increase by tiny amounts too small to notice in a lifetime, but immense over cosmic history. Somewhere, light from a galaxy at the edge of the observable universe is being stretched as it travels, each wave elongated by the growth of space. That stretching is both a record of the past and a glimpse of the future. It's the signature of a cosmos still in motion, still accelerating into the unknown. And though the future remains uncertain, the pattern is clear. The universe has changed its pace before, and it may change again. Each shift reshapes the cosmos, rewriting the relationships between its forces, its structures, and perhaps even its destiny. The slowing was gravity's era. The speeding is dark energies. The unknown, whatever comes next, will belong to something beyond both, something that may redefine what expansion even means. For now, we can only follow the light, measure the redshifts, and listen to the faint hum of the cosmos as it races outward. Somewhere in that hum, in the balance between slowing and speeding, lies the answer to how long the universe will continue to expand, and whether that expansion will ever stop. And as we look further into the possibilities, we begin to see the outlines of those potential endings, the ways the story might unfold depending on how the forces play out. Will everything drift apart into eternal silence? Will it collapse back into itself? Or will it tear apart entirely? The possibilities are many, and each one paints a different picture of how forever might end. That's where the story leads next, into the future itself, into the possible fates of everything, and the quiet question that lingers behind them all: when will the universe stop expanding? When you think about the future of the universe, it's easy to imagine a vast stillness, a place so large and so ancient that change becomes impossible. But even the cosmos has a future. It may be slow, stretching beyond comprehension, but it exists, written into the laws that govern its expansion. Every galaxy, every particle, every flicker of light carries within it a clue about what is yet to come. The universe is not frozen, it is evolving, and that evolution leads inevitably toward one of several possible fates. The path the universe takes depends entirely on how the balance between gravity and expansion unfolds. If gravity remains strong enough, it might one day pull everything back together. If dark energy continues to dominate, the expansion might go on forever, slowly erasing structure and light. And if dark energy grows stronger over time, the universe could meet a more violent end, one where even atoms are torn apart. Each of these possibilities paints a different picture of what the distant future might look like. None of them are certain, but all of them are grounded in the same fundamental question: what happens when space itself refuses to stay still? The scenario most cosmologists consider the most likely, based on current evidence, is a universe that expands forever, the so-called Big Freeze. It's not an explosion, not a sudden end, but a long, slow fading of all things. As space continues to stretch, galaxies drift farther apart. The light from each one grows dimmer, stretched into longer and longer wavelengths until it disappears beyond detection. Over billions of years, the stars within each galaxy burn through their fuel and die. The bright, crowded sky we see today would grow sparse. New stars would stop forming. Old ones would fade into embers, and the night would grow darker than ever before. Even this process would take an almost unimaginable length of time. The younger stars forming today could burn for trillions of years before their light finally fades. White dwarfs, the remnants of smaller stars like our Sun, would cool slowly, turning from glowing embers to cold, dark remnants. Neutron stars and black holes would remain as the last visible objects, isolated in an increasingly empty universe. As the expansion continues, galaxies that are not gravitationally bound to each other will slip beyond each other's horizons. Their light will never reach one another again. Each galaxy will become an island, alone in the vast sea of space. For observers living in one of those distant futures, if any beings are left to observe, the universe will appear static once more. The cosmic background radiation, the faint afterglow of the Big Bang, will cool until it is undetectable. The evidence of the universe's origin and expansion will vanish. It will seem, once again, like an eternal and unchanging cosmos. Over even longer timescales, the stars that remain will die quietly. Without new ones forming, the galaxies will go dark. Black holes, the most enduring structures in the universe, will dominate for a while, but even they are not eternal. Through a process known as Hawking radiation, black holes can slowly evaporate, losing mass over immense spans of time. The larger the black hole, the longer it takes. The most massive ones, those at the centres of galaxies, could take up to 1089 years to evaporate completely. After that, the universe would enter what physicists call the degenerate era. With no stars, no galaxies, no bright sources of energy, space would be filled only with remnants, stray particles, photons, and fading traces of radiation. The temperature would approach absolute zero, and time would stretch into meaninglessness. In this endless stillness, expansion would continue, but there would be nothing left to expand. That's the big freeze. Not an ending in fire or collapse, but in quiet, a universe that simply runs out of things to do. But this future depends on an assumption, that dark energy remains constant. If it stays the same, expansion continues at an accelerating but steady pace, leading eventually to cold emptiness. Yet the universe has surprised us before. If dark energy were to change, if its strength increased over time, the story could be very different. In that case, expansion wouldn't just continue, it would accelerate exponentially, growing faster and faster until it overwhelmed everything, even the forces that hold matter together. This is the scenario known as the Big Rip. In the Big Rip, space itself stretches so quickly that no structure can survive. At first, distant galaxies drift away from each other faster than light, disappearing beyond reach. Then, as acceleration increases, the gravitational bonds within galaxies fail. Stars drift apart. Planets lose their orbits. Eventually, even the atoms themselves are pulled apart, their particles separated by the unstoppable expansion of space. It's a terrifying thought, but it's not chaotic or explosive. It's the geometry of space itself changing faster than anything can resist. The timeline for such an event, if it were to happen, would depend on how fast dark energy's influence grows. If its density increases steadily, the Big Rip could occur in tens of billions of years. That might sound distant, but on a cosmic scale, it's a blink. It would begin subtly, with galaxies vanishing one by one, then stars pulled from their systems, then the fabric of matter itself unravelling. Everything would end not with a bang, but with the quiet tearing of space at every point. There's no current evidence that dark energy behaves that way, but the possibility remains open. It's a reminder of how fragile our understanding still is. We know that expansion is accelerating, but not whether that acceleration will stay constant. For now, observations suggest that dark energy behaves like a cosmological constant, unchanging over time. But if that ever changes, even slightly, the universe's fate could shift dramatically. There's another possibility, one that reverses the story entirely. If dark energy were to weaken or reverse sign, turning from repulsive to attractive, expansion could slow, stop, and then reverse. The universe could begin contracting, galaxies moving toward each other, distances shrinking instead of growing. Over time, everything would collapse inward, the temperature and density rising again, perhaps leading to another singularity. This scenario is known as the Big Crunch. In the Big Crunch, the universe's future mirrors its past. Expansion halts, and gravity reclaims its dominance. The galaxies that once drifted apart begin to fall back together. Over billions of years, the sky would grow brighter again, filled with the glow of merging galaxies. Temperatures would rise as matter compressed, and eventually the universe could collapse into a state as hot and dense as it was at its beginning. Whether that would mark an end or a new beginning is an open question. Some theories suggest that such a collapse could trigger another expansion, a new Big Bang, in a cyclic pattern of birth and rebirth. Others see it as a final singularity, a universe collapsing into itself for the last time. The idea of a cyclic universe has deep roots in both physics and philosophy. Some ancient traditions imagine the cosmos as eternal, endlessly renewing itself. In modern cosmology, that idea takes mathematical form. If the universe's expansion is governed by changing forms of dark energy, or by hidden dimensions beyond our own, then each collapse could be followed by another burst of creation. Space could oscillate forever, expanding and contracting like a cosmic heartbeat. It's a beautiful idea, though still speculative. The evidence for it remains uncertain, and current observations of dark energy make it seem unlikely, but not impossible. Each of these possible futures, the freeze, the crunch, the rip, and the cyclic, arises from the same basic physics, applied in different ways. The difference lies in the details of dark energy, gravity, and time. If dark energy stays constant, the big freeze awaits. If it strengthens, the big rip. If it weakens or reverses, the big crunch. And if the laws themselves allow it, perhaps a universe that renews itself endlessly. There are even stranger possibilities, ones that reach beyond the boundaries of current theory. Some physicists suggest that the vacuum of space might not be perfectly stable. If a lower energy state exists somewhere in the quantum landscape, the universe could, in principle, transition to it, a process known as vacuum decay. If that were to happen, a bubble of new vacuum could form and expand at the speed of light, rewriting the laws of physics within it. Every particle, every atom, every structure would vanish in an instant, replaced by a new form of space with different constants and forces. It's purely theoretical, and there's no evidence that such an instability exists, but it's another reminder of how little we truly know about the fabric of reality. Even the idea of end becomes blurry when you consider how time behaves on cosmic scales. In a universe that expands forever, time stretches endlessly. Events slow, energy fades, and processes that once defined motion cease to matter. The distinction between before and after loses meaning. In a sense, eternity becomes a kind of stasis. In a collapsing universe, the opposite happens. Time accelerates toward a singularity, everything compressed into a single final moment. The difference between these fates is not just physical, but philosophical. One ends in silence, the other in compression, but both lead to transformation. It's easy to hear these possibilities and feel a kind of melancholy. Each one seems to erase everything: galaxies, stars, even memory. But they also reveal something extraordinary. that the universe, even in its final forms, is a process, not a place. Whether it ends in ice, fire, or rebirth, it's always changing, always moving. Its fate is not static. It's a continuation of the same motion that began with the first expansion. The same breath, now exhaling across eternity. Even the big freeze, the quietest of fates, holds a strange beauty. Imagine a universe trillions of years from now, where the last star flickers out and darkness returns. Space would be silent, but not dead. It would still expand, still evolve, still carry traces of its past in the faintest quantum ripples. And in that silence, the laws of physics would continue to operate, simple and precise. The universe wouldn't end with a sound or a boundary, but with continuation. An infinite, steady fading that never quite stops. When cosmologists model these futures, they're not predicting in the sense of prophecy. They're exploring possibilities, guided by equations and observation. Each scenario is a map of how the universe might behave under certain conditions. The truth could be something none of us can yet imagine. Perhaps dark energy is not constant, but a sign of something deeper, a new layer of physics waiting to be uncovered. Perhaps there are interactions between dark matter and dark energy that we haven't seen yet, changing the story in ways subtle but profound. The point is not that any one model must be right, but that all of them show how expansion, once begun, will always lead to transformation. The cosmos doesn't need to end for its story to be meaningful. Its meaning lies in the fact that we can trace it at all, that beings made of stardust can measure the stretching of space, read the faint light from the past, and imagine the future of everything. Whether the universe ends in cold, collapse, or rebirth, we are part of its motion. We are temporary expressions of its balance between gravity and expansion, flickers of awareness born from that same process. So when you think about the universe's fate, don't think of it as doom. Think of it as continuation, the next step in a process that has never stopped since the beginning. Expansion is not something the universe does. It's what the universe is. It grows, it evolves, it changes, and one day it will reach whatever comes next. That next stage may be silent, may be unrecognizable, but it will still be part of the same story. The story of a universe that has always been in motion. What will that endless expansion feel like as time stretches forward into the cold, quiet eras to come? What will it mean for light, for matter, for the traces of life that once looked up at the stars and wondered how it would all end? The future of the universe is not a dramatic one. It is not a sudden end or a collapse. It is a gradual quieting, a long and patient dimming that unfolds over uncountable ages. When cosmologists speak of the big freeze, they're not describing a single event but a process. It is the continuation of what's already happening all around us, expansion, cooling, and the slow thinning of matter. The universe is still young by its own standards. The stars are still burning, galaxies still collide, and light still fills the dark. But every second carries us closer to a quieter cosmos, a universe that gently fades into stillness. Right now, expansion defines everything on large scales. Galaxies drift farther apart, their light stretching into longer wavelengths as space grows. But within galaxies, gravity still holds strong. Stars orbit their centers, planets circle their stars, and life exists in small, warm pockets of order. The night sky above Earth is still bright with the combined glow of billions of suns. In cosmic terms, this is an age of light, a time when energy is abundant and the universe is filled with structure. But even as the stars shine, their fuel is being spent. Hydrogen, the simplest and most abundant element, burns in stellar cores, fusing into helium. Over time, that fuel runs out. Some stars die quickly in supernovae, scattering heavy elements into space. Others fade quietly into white dwarfs. The balance of gravity and radiation that keeps a star alive eventually breaks. This process is ordinary, predictable, and universal. Every star, no matter its size, must one day end. In a few billion years, even our own sun will exhaust its core hydrogen. It will swell into a red giant, shedding its outer layers and leaving behind a dense white dwarf, a core roughly the size of Earth, glowing faintly from residual heat. Around the same time, most stars of similar mass across the galaxy will reach the same fate. New stars will still form from clouds of gas and dust, but the supply of raw material will begin to dwindle. Every generation of stars uses up more hydrogen, locking it away in heavier elements and remnants. Eventually there will be no fresh fuel left. Star formation will slow, then stop altogether. That moment, when the last stars form, marks the transition into what astronomers call the degenerate era. It won't arrive for trillions of years, long after every galaxy we can see today has drifted far beyond the reach of any observer in ours. The expansion of the universe will continue throughout, carrying the galaxies away, stretching light to invisibility. The night sky, once dense with stars, will become sparse. The familiar constellations will distort and disappear. The Milky Way and Andromeda, long since merged into a single elliptical galaxy, will be an isolated island adrift in dark space. For a while it will still glow faintly. Billions of white dwarfs, neutron stars and faint red dwarfs will keep shining, though dimly. These stars will live for extraordinary spans of time. Red dwarfs, the smallest and coolest stars, burn their fuel so slowly that they can last for trillions of years. Some will still exist when the universe is 1,000 times older than it is today. Their light will be faint but persistent, soft pinpricks in a sky growing ever darker. Eventually, even those last stars will exhaust their fuel. They'll cool into black dwarfs, cold, dead spheres radiating only the faintest heat. There will be no new stars to replace them, no more supernovae to scatter heavy elements. The galaxies will be silent, filled only with remnants. The universe will be darker than it has ever been, but it will not yet be empty. Matter will still exist, just colder, slower, and lonelier. Over even longer timescales, gravity will continue its quiet work. Stellar remnants will drift and collide. Some may merge, momentarily flaring back to life as new sources of heat. Others will fall into black holes, feeding them briefly before disappearing. Black holes themselves will dominate this era. The largest, those at the centres of galaxies, will continue to draw in stray matter and smaller black holes. They will grow slowly over quadrillions of years. But even black holes are not eternal. Quantum mechanics predicts that they emit radiation, an effect known as Hawking radiation. It's an almost unimaginably slow process, but over immense spans of time, it means that black holes can evaporate. The smallest ones go first, disappearing relatively quickly. The largest, the supermassive black holes weighing billions of solar masses, could take around 1099 years to vanish. When they do, they will end not in collapse but in release, a faint burst of radiation marking their final moments. By then, the universe will have cooled to near absolute zero. The cosmic microwave background, the relic light from the Big Bang, will have stretched into wavelengths longer than the size of galaxies. Its temperature will be so low that it will be indistinguishable from the cold vacuum itself. Space will continue to expand, but there will be nothing left to fill it with structure. The particles that remain, stray electrons, protons, neutrinos, will become rarer and rarer. Some will decay, depending on the laws of physics that govern them. The proton, for instance, may not be truly stable. If it decays, it would transform into lighter particles over incredibly long periods, perhaps around 1034 years or more. If that happens, even the most basic building blocks of matter will eventually vanish. The universe will lose not just light, but substance. By that stage, the universe would be unrecognizable. There would be no galaxies, no stars, no atoms, no light. The expansion of space would continue, but it would be meaningless to speak of distance. The few remaining particles, separated by vast emptiness, would rarely, if ever, interact. The cosmos would become a thin mist of low-energy radiation, expanding endlessly toward infinite dilution. This is the Big Freeze, not an ending with destruction, but with exhaustion. A universe that has simply run out of energy gradients, out of ways to do work, out of difference. Thermodynamics calls this heat death, the point at which entropy reaches its maximum and all processes stop. There would be no more stars to shine, no more galaxies to move, no more contrast between hot and cold. The cosmos would become uniform, static, and eternal in its stillness. It's difficult to imagine such a state because everything we know, life, motion, perception, depends on contrast. We exist because there is warmth and cold, light and dark, energy flowing from one form to another. Without those differences, time itself loses meaning. In the Big Freeze, time would continue mathematically, but nothing would change. It would be an eternity without events, without motion, a universe that is still, but not ended. To some, this fate sounds bleak. The idea that everything will fade into cold emptiness can feel like loss. But there's another way to see it. The Big Freeze is not a tragedy, it's a completion. Every process that ever began will have run its course. The stars will have lived full lives, their energy spread across the cosmos. The materials that once formed planets, oceans, and living things will have returned to the background. The universe will have done what it was meant to do: transform energy into structure, structure into motion, motion into stillness. In that far future, there will be no observers left to measure expansion. The speed of light will still define the boundaries of space, but nothing will remain to see it. The universe will have no memory of its brightness, no trace of the galaxies that once filled it. Yet in a very literal sense, nothing is ever truly lost. Energy cannot be destroyed. It only changes form. The light that once filled the universe will still exist, stretched into wavelengths so long that they become indistinguishable from space itself. The cosmos will be filled with the faintest hum of energy, spread evenly across infinity. Even in that quiet future, quantum processes might continue on microscopic scales. Particles may flicker in and out of existence through quantum fluctuations. Tiny pockets of space might, by chance, produce brief bursts of energy, miniature big bangs that momentarily create new regions of space-time. Some cosmologists have suggested that these fluctuations could, in principle, give rise to entirely new universes. If that's true, then even the Big Freeze might not be final. The end of one universe could be the seed of another. But whether or not such rebirths occur, the Big Freeze remains the simplest outcome of the physics we know. It doesn't require new laws or exotic forces. It's the natural result of expansion continuing indefinitely. Everything spreads out, cools, and settles into equilibrium. It's a universe that ends not in chaos, but in peace. There's a kind of comfort in that vision. The same universe that began in unimaginable heat and violence will end in quiet. The same laws that created stars and galaxies will bring about their fading. There's symmetry in that, not the symmetry of repetition, but of completion. The cosmos will have lived through every stage of its existence, from birth to calmness, from energy to stillness. Right now we exist in a brief and luminous phase, a moment of brightness between two eternities of dark. The early universe was filled with blinding radiation. The far future will be filled with near silence. We live in the middle during the age of stars. It's an age that allows structure, life, and thought. Every galaxy shining in the night sky is a participant in this fleeting moment of light, a moment that spans billions of years but will one day pass. When you think of the Big Freeze, you can think of it not as an erasure, but as the slow closing of the universe's eyes. The stars that once burned brightly will cool and rest. The galaxies that once danced across the void will drift apart and settle. The light that once filled the cosmos will stretch into invisibility. And in that stillness there is no pain, no loss, no violence, only quiet. Somewhere, even in that distant time, the memory of expansion will remain encoded in the fabric of space. The universe will still carry the faint imprint of its beginning, the curvature, the ratios, the traces of its evolution. It will still be the same universe, only older, gentler, and at peace with itself. That's the strange grace of the Big Freeze. It's not a story of destruction, but of rest. The universe doesn't die, it finishes. It completes its transformation from fire to calm, from something to everything, from everything to nothing, and from nothing back into the quiet potential that has always been there. And as we follow that thread through time, it's natural to wonder, if this quiet fading awaits us, could there also be a time when the process reverses? Could gravity ever gather what's left and begin again? Could expansion stop, turn, and draw the universe back into itself? The idea of the universe ending in cold stillness feels almost inevitable when you hear about expansion and dark energy. Yet, for much of scientific history, the opposite was believed to be true. For decades, many cosmologists thought the universe might not drift into silence at all, but instead collapse. A vast contraction that would bring everything back together. This vision, known as the Big Crunch, imagines the cosmos not as a one-way journey into emptiness, but as a breathing entity, one that expands, slows, and eventually draws itself inward again. To understand this possible future, it helps to step back and remember what expansion really is. The universe isn't growing into anything. Space itself is stretching, carrying galaxies apart with it. The rate of that expansion depends on how much energy and matter exist, and how they interact through gravity. If gravity was strong enough, if there were enough matter in the universe, it could eventually overcome expansion, slowing it to a stop and then reversing it. Space would begin to contract, galaxies would drift closer, and the universe would start collapsing inward. That reversal is what defines the Big Crunch. It's the mirror image of the Big Bang, an inverted process in which everything that once moved apart begins to come together again. The expansion that began more than 13 billion years ago would not go on forever. It would reach a turning point, a kind of cosmic peak, and from there, everything would begin to fall back toward everything else. In the early days of cosmology, before dark energy was discovered, this seemed like a plausible fate. Observations showed that expansion was slowing, which made sense if gravity was pulling back against it. Scientists spoke about the universe's critical density, the exact amount of matter and energy needed to determine its future. If the density was above that threshold, gravity would eventually halt expansion. If it was below, expansion would continue indefinitely. The universe appeared to be finely balanced, close to that dividing line. The Big Crunch seemed not only possible but likely. In that scenario, expansion would gradually decelerate over billions of years. Galaxies that are now rushing away from each other would slow their motion. The distances between them would stop increasing. Eventually, the pull of gravity would win. The direction of motion would reverse. Galaxies would begin moving toward each other, the universe contracting at first slowly, then faster and faster. The cosmic web would tighten, filaments collapsing into dense knots of matter. As contraction continued, the night sky would grow brighter instead of darker. Galaxies would merge more often, collisions becoming commonplace. Stars would ignite in bursts of new formation as gas clouds compressed under gravity. For a time, the universe might experience a brief resurgence of light, a second golden age of stars. The cosmic background radiation, now faint and cold, would grow warmer as the universe compressed and heated. The temperature would rise, the density would increase, and the universe would begin to resemble its early state again, only in reverse. This process would unfold over extraordinary timescales. Even as galaxies merged, the laws of physics would remain unchanged. Gravity would dominate, accelerating the contraction. In a sense, the universe would be replaying its beginning backward. Distances would shrink, energy would concentrate, and space itself would curve inward. The horizon, the limit of what could be seen, would shrink as well, since light would have less and less distance to travel before encountering itself again. Eventually, as contraction continued, temperatures would rise into the millions of degrees. Radiation would dominate once more, overwhelming matter. Atoms would break apart into plasma. The background radiation, once stretched into microwaves, would shift back to visible and then ultraviolet wavelengths. The entire universe would glow again, just as it did after the Big Bang, but now in its final moments before collapse. At the peak of contraction, everything, galaxies, stars, particles, would converge toward a single point of infinite density, a singularity. Space and time would curve so sharply that the distinction between before and after would blur. In that instant, the universe would, in a sense, end. But whether that end would truly be final is another question entirely. Some cosmological models suggest that a universe collapsing in this way might not stop at the singularity. Instead, the extreme conditions could trigger a rebound, a new expansion born from the old contraction. Space could bounce outward again, beginning another cycle of growth and cooling. In that view, the Big Crunch wouldn't be an ending but a transition, one beat in an infinite cosmic rhythm. The universe could expand, contract, and expand again endlessly, with each cycle giving rise to a new configuration of stars, galaxies, and perhaps even new laws of physics. This concept, often called the cyclic or oscillating universe, is deeply compelling. It suggests that time itself could be circular on the grandest scale, that the cosmos never truly dies but continually renews itself. Each collapse could seed a new creation, each ending becoming a beginning. The energy of contraction could fuel the next expansion, keeping the cycle going forever. For a long time, that idea appealed not just scientifically but philosophically. It resolved the discomfort many felt at the thought of a universe with a definite beginning or end. If the cosmos breathes forever, there's no first cause, no final silence, only continuity. It also mirrors patterns we see everywhere else in nature: birth, growth, decline, renewal. The universe, in this view, participates in that same rhythm, but on a scale so vast that even eternity becomes just one more cycle. However, the discovery of dark energy complicated this picture. The accelerating expansion we observe today makes a future contraction seem unlikely. If dark energy continues to dominate, space will never stop stretching. The density of matter is far below the critical threshold needed to reverse expansion. Gravity, it seems, will never again gain the upper hand. Still, cosmology is a science of patience. The universe is young compared to the timescales of its fate. Dark energy might not remain constant. It could change, fade, or even reverse. If it does, the path toward a Big Crunch might reopen. The physics of such a reversal would be extraordinary. If dark energy weakened, the expansion would slow. Galaxies that are now receding could begin to approach one another again. The cosmic microwave background would grow warmer, the average density of matter would increase, and gravity's influence would strengthen. Over immense stretches of time, the overall curvature of space could shift from flat to closed, meaning that parallel lines would eventually meet, and the universe would have a finite volume once more. From that point on, contraction would accelerate. The distances between clusters and galaxies would shrink. Collisions would become inevitable. In a sense, the universe would look the same as it once did, chaotic, filled with mergers and bursts of energy, but now heading toward convergence instead of dispersal. The closer everything gets, the faster the contraction becomes. Gravity feeds on density. As the universe grows denser, the pull increases. The process accelerates until the entire cosmos collapses inward. If you could somehow observe it from the outside, which of course is impossible, you would see the universe shrinking, its light blue shifted instead of red shifted, its energy growing more intense with every moment. Eventually, even black holes would merge, forming enormous singularities that dominate the final moments of collapse. Matter and radiation would intermingle in a blazing sea of energy. The laws of physics as we know them would begin to break down. Time, tied to the expansion of space, would lose its familiar meaning. The universe would approach the same conditions that existed at its birth: infinite density, infinite temperature, infinite curvature. At that point, two possibilities remain. The first is finality, a true collapse in which time and space end. The second is renewal, a bounce, a new beginning. The latter is speculative but deeply studied in theoretical cosmology. Quantum gravity, a field that seeks to reconcile general relativity with quantum mechanics, suggests that the singularity might not be absolute. Instead of a single point, the universe might reach a minimum size and then rebound. In some models, the energy of the collapse is converted into expansion energy for the next universe. The Big Crunch becomes the Big Bang of the next cycle. If that were true, the universe would be far older than we think. Not 13 billion years, but timeless, without beginning or end. Each cycle would erase the memory of the one before it, resetting entropy and beginning anew. The light from previous cycles would vanish, replaced by the radiation of the next. It would mean that even after everything collapses, the cosmos doesn't stop. It transforms. This cyclic vision has evolved through many versions. In earlier decades, it was imagined as a simple oscillation, with the universe expanding and contracting like a pendulum. In more recent theories, influenced by ideas from string theory, each cycle could occur in a higher dimensional space, with collisions between branes, multi-dimensional surfaces, triggering each new Big Bang. In these models, the Big Crunch isn't a catastrophe, but an act of creation. Of course, we don't know whether any of this will happen. The evidence for dark energy's persistence makes the Big Crunch unlikely, at least with what we know today. But the possibility remains a powerful reminder that the universe may still hold surprises. The equations of general relativity allow for contraction as easily as expansion. If the underlying conditions change, if the sign of the cosmic pressure reverses, then everything we know could begin to fall inward. Even as a hypothetical, the Big Crunch offers something profound. It shows that the cosmos could be self-contained, that its story might loop back into itself. It also reflects an underlying symmetry. Expansion and contraction are not opposites, but complementary phases of the same process. One disperses matter and energy, the other gathers them. One cools the universe, the other heats it. Together they describe a complete cycle of transformation. There's also something oddly human in the notion of a universe that breathes. Every inhale and exhale, every rhythm of life mirrors the same pattern: expansion, contraction, renewal. The universe doesn't live as we do, but it follows the same natural principle. Energy moves outward, then inward, seeking balance. The Big Crunch, if it were to happen, would be the universe finding its balance again. If it does happen, the final moments would be beyond imagination. Every particle, every photon, every remnant of structure would converge toward a single, unified state. The energy density would be so great that the distinctions between matter and radiation, between time and space, would blur. It would be the end of one form of the universe and perhaps the beginning of another. And even if the Big Crunch never occurs, its idea remains valuable. It reminds us that expansion is not destiny, that the cosmos could still surprise us. It's a mirror held up to the Big Freeze, showing the opposite extreme. Not a universe fading into silence, but one roaring back into heat and light. Both are governed by the same laws. Both are outcomes of the same expansion that began with the Big Bang. The difference lies only in how those laws unfold over time. The universe, after all, has changed its behaviour before. It once slowed, then began accelerating. It might change again. We live in one brief epoch, in one pattern of forces, in one arrangement of energy. Beyond our horizon, beyond our future, those patterns might evolve. And if they do, the universe might one day turn inward again, breathing in as gently and inevitably as it once breathed out. If that happens, there would be no explosion, no sound, just the growing warmth of space itself, light intensifying, matter compressing, the cosmic background glowing once more. In that moment, expansion and contraction would meet, indistinguishable from each other. The universe would return to where it began, not as repetition, but as completion. And from that completion, if the laws of nature allow it, another universe might be born. The universe, for all its vastness, seems steady to us. Galaxies drift apart, stars live and die, and the large-scale structure of space looks unchanging over human lifetimes. But beneath that quiet stability, there's a hidden tension. Expansion isn't a fixed process. It's driven by something deeper, an invisible pressure within space itself. For now, that pressure is gentle. It stretches galaxies apart slowly, imperceptibly. But what if it doesn't stay gentle? What if the same force that now guides expansion began to grow stronger with time? What if it didn't just push galaxies apart, but pulled the very fabric of the universe apart at every level? That's the idea behind what scientists call the Big Rip. It's not an explosion or a collapse, but a runaway stretching. A future in which dark energy's influence increases until it overwhelms everything. Space itself becomes unstable. The distances between galaxies grow at an accelerating rate, faster and faster, until even the most tightly bound structures can no longer resist. It's a scenario that takes the quiet acceleration we observe today and projects it forward to its most extreme conclusion. To imagine it, picture the expansion we see now. The universe grows larger every second, but the rate of that growth is measured by something called the scale factor, a number that describes how much space has stretched since the Big Bang. In the standard model of cosmology, this scale factor increases smoothly, with the acceleration driven by dark energy remaining roughly constant. But if dark energy were to strengthen over time, the scale factor would grow explosively. The expansion rate would diverge toward infinity within a finite period. That means the universe could reach a state of infinite size, or, more accurately, infinite separation, after only a calculable amount of time. This idea comes from a particular kind of dark energy model, one in which the energy density of the vacuum increases as space expands. In most cosmological models, the energy density of dark energy remains constant. That's the cosmological constant Einstein introduced. But if the equation of state parameter, often represented as doubled, drops below 1, the energy density actually increases as space grows. The result is what physicists call phantom energy. It doesn't just counteract gravity, it dominates it completely, leading to exponential, unstoppable acceleration. The Big Rip is the ultimate consequence of that kind of universe. It's not something that would happen suddenly. It would begin subtly, far in the future, as expansion continues to accelerate. Galaxies that are already receding from one another would move away faster and faster. Over billions of years, light from them would redshift beyond visibility. The cosmic horizon, the boundary of what can ever be seen or affected, would shrink as more and more of the universe became unreachable. Eventually, even nearby galaxies outside our local gravitational group would drift beyond that horizon. The night sky would begin to empty, but the process wouldn't stop there. As dark energy's influence grew, it would start affecting smaller scales, not just the space between galaxy clusters, but the space within them. The galaxies themselves, which have remained gravitationally bound since their formation, would begin to feel the strain. Their stars would drift apart. pulled away by expansion faster than gravity could hold them. The Milky Way, the Andromeda Galaxy, and all the smaller companions that make up our local group would separate. Over time, even individual solar systems would begin to unravel. The timeline for this kind of future depends on how quickly dark energy strengthens. If the universe follows the simplest phantom energy model where W stays below, one but constant, cosmologists can calculate the approximate sequence of events. The end wouldn't come all at once. It would unfold in stages, each one marking a new level of disintegration. Galaxies would dissolve billions of years before the final moment. Solar systems would unbind millions of years before. Planets would drift from their stars, atoms would come apart, and finally even the fabric of space itself would tear. As expansion accelerated, every bond that holds matter together would face increasing strain. At first, only the weakest, the gravitational bonds between galaxies, would fail. Then the stronger ones, the gravitational ties within galaxies and between stars and planets. But dark energy, growing unchecked, would continue increasing its pull until it began to affect even the electromagnetic forces that hold atoms together. The distances between atomic nuclei and their electrons would grow. Molecules would disintegrate. Matter itself would lose its coherence. The final stages would be beyond anything familiar. As the scale factor raced toward infinity, time intervals between major events would shrink. 1 billion years before the end, galaxies would dissolve. A few million years before, stars would drift away from each other. Hours before the final moment, planets would disintegrate. Seconds before, atoms themselves would be ripped apart. Then, at the last instant, the very structure of space-time would become unstable. Distances would lose meaning. Every point in space would recede from every other point at an infinite rate. In that instant, the universe would, in a sense, cease to exist. It's hard to describe what cease to exist means on that scale. There wouldn't be an explosion or a collapse. There would be no light, no sound, no energy release in the conventional sense. It would simply be that the metric of space, the framework that defines distances and times, would diverge. The universe wouldn't end inside itself. It would end as itself. There would be no space left to expand, no time left to pass. The story of the cosmos would stop not with an event, but with the loss of the very fabric that makes events possible. What makes the Big Rip so unsettling is that it's a direct extension of what we already observe. We know expansion is accelerating. We know dark energy drives that acceleration. The only question is whether that energy remains constant or changes over time. If it's constant, the universe coasts into the Big Freeze. If it grows stronger, the Big Rip follows. The difference lies only in the behavior of one parameter, one small number in the equations of cosmology. A fraction above or below one changes everything. There's no evidence yet that dark energy behaves this way. Observations from the Planck satellite, from supernovae, and from large-scale galaxy surveys all suggest that W is close to 1, perhaps exactly 1. But the margin of uncertainty is wide enough that the possibility remains open. We can't yet rule out a phantom future. That uncertainty keeps the Big Rip on the table, unlikely but not impossible. Even if it never comes to pass, the concept has deep implications. It forces scientists to confront what it means for space to be something that can change, stretch, and even destroy itself. In classical physics, space was the stage on which events unfolded. In modern cosmology, space is the event. Its expansion and contraction aren't things happening within it. They are what define reality. The Big Rip is, in that sense, the most extreme expression of this principle. Space expanding so violently that it undoes the very things that give it meaning. It also reveals a strange symmetry across all possible cosmic fates. The Big Freeze ends in stillness. The Big Crunch ends in compression. The Big Rip ends in fragmentation. In each case, the universe loses structure, through cooling, collapsing, or tearing apart. Entropy reaches a maximum and information disperses. No matter how the story goes, the end is a kind of equilibrium, whether through silence, heat, or disintegration. For all its violence, the Big Rip wouldn't feel violent to anyone experiencing it, if anything could experience it. The change would happen so gradually over cosmic timescales that no being, no planet, no star would notice until the very end. Each step would seem static in its own frame, even as the universe raced toward dissolution. It would be like watching the tide rise so slowly that it appears still, only to realize much later that the shore is gone. In that way, the Big Rip is almost a philosophical idea as much as a physical one. It's about what happens when infinity intrudes into the finite. Space becomes infinite in a finite time. Distances become meaningless. Time itself stops having continuity. It's a reminder that the laws we take for granted, the stability of atoms, the strength of forces, the constancy of physics, depend on a balance that could, in principle, shift. Some theorists have even explored what might come after a Big Rip, if such a term even applies. Could a new space-time emerge from the torn fragments of the old? Could quantum effects smooth out the singularity of infinite expansion and give rise to a new, smaller universe? These are speculative ideas, but they reflect a deeper truth, that even in imagining destruction, cosmology imagines transformation. The universe has always evolved through change, and if it ends, it may do so by changing again, in ways we cannot yet conceive. It's striking how the most extreme scenarios, the Big Crunch and the Big Rip, mirror each other. In one, gravity wins completely. Everything falls inward. In the other, expansion wins completely. Everything is pulled apart. They are opposites in form but identical in consequence. A universe brought to a point of singularity, a limit beyond which known physics fails. The symmetry between them is not just mathematical, it's a reminder that balance defines existence. The universe exists because neither force has yet won. It's the tension between gravity and expansion that gives structure, motion, and time. Right now, that tension still holds. Galaxies remain intact, stars continue to burn, and local gravity still overcomes cosmic expansion. The Milky Way, Andromeda, and their smaller companions will merge into a single galaxy long before any hypothetical Big Rip begins. Even as the larger universe grows emptier, these local structures will stay bound for tens of billions of years. The future, in other words, still has time. But if dark energy grows, even that time has an end. At some far future moment, if phantom energy exists, no amount of gravity, no strength of bond, no force of nature will be enough. Expansion will not simply move galaxies apart. It will reach into every atom, every field, every corner of reality. It will not just separate things. It will erase the meaning of separation. There will be no space to measure, no time to pass, no observer to watch. The universe will end not with collapse or stillness, but with fragmentation into infinite distance. And if that day comes, it will be the last movement of a process that began long ago, with the same expansion that gave rise to everything we know, the same force that allowed stars to form, galaxies to grow, and life to exist would become the force that ends it all. There's something deeply symmetrical in that. Not cruel, not tragic, but balanced. The universe would have completed the full arc of its motion, from singularity to singularity, from creation to dissolution. If the Big Rip ever happens, it will mark not just the end of space, but the end of laws. The constants of nature that have governed everything, gravity, electromagnetism, the nuclear forces, would lose their coherence as space itself disintegrates. What lies beyond that is unknowable. Perhaps new laws would emerge, as they did after the Big Bang. Perhaps nothing would. The equations end there, and with them all prediction. Yet even that unknowability is part of what makes the universe so fascinating. Every possibility, stillness, collapse, unravelling, reflects the same underlying truth, that change is the universe's only constant. It began by expanding, and it may end the same way, expanding beyond all limits, until expansion itself can no longer be defined. In that sense, the Big Rip isn't just a physical theory. It's a reminder that everything, even the most stable reality, is temporary. The stars we see, the galaxies we map, the very notion of space and time, all are part of a dynamic, evolving cosmos. Nothing in it stands still forever, and just as the Big Freeze represents the universe falling asleep, and the Big Crunch represents it waking again, the Big Rip would be the moment of unmaking, the instant when the dream itself dissolves. It's the quietest and most complete form of impermanence, where everything returns not to nothing, but to separation beyond measure. Somewhere, in the farthest reaches of time, that possibility lingers. Whether it ever comes to pass or not, it tells us something about where we are now. Balance between extremes, living in the middle of a process that has neither begun nor ended, carried forward by the same expansion that may one day erase it. And as we follow that expansion through its possible fates, freeze, crunch, or rip, we're left with one question that transcends them all. If the universe ends in any of these ways, does that truly mean it ends? Or could something else, something beyond our present understanding, follow? When we imagine the end of the universe, whether it fades into the cold silence of the Big Freeze, collapses inward in the Big Crunch, or tears apart in the Big Rip, the question that lingers is the same. What comes after? Does the universe stop completely, leaving only emptiness? Does it begin again? Or is the very idea of after meaningless, once space and time themselves have reached their limits? These are not questions with answers, but they are questions that arise naturally when we follow the story of the cosmos to its horizon. At first glance, the end of the universe seems absolute. Each of the great fates, freezing, collapsing, unravelling, appears to leave no room for continuation. In the Big Freeze, everything is stretched beyond interaction. In the Big Crunch, everything collapses into a singularity. In the Big Rip, even atoms are torn apart. Yet the more physicists have studied the laws of nature, the harder it has become to imagine a true end. Energy cannot be destroyed. Information, according to quantum theory, cannot simply vanish. If those laws hold under all circumstances, then something must persist, even when the universe seems to have reached its conclusion. The difficulty is that at such extremes, the laws we know no longer apply cleanly. General relativity, which describes the structure of space-time, breaks down at singularities. Quantum mechanics, which governs the smallest scales, has no clear way to describe the universe as a whole. At the end, or the beginning, of time, the two frameworks must meet. The search for what happens beyond that point is, in many ways, the search for a theory that unites them. Physicists sometimes refer to this unknown frontier as the domain of quantum gravity. It's the realm where space-time itself becomes quantized, where space and time are not continuous, but made of discrete units, like the pixels of a digital image. In that regime, the smooth fabric of the universe becomes grainy. The singularities of general relativity, the points of infinite density where equations break down, might not exist at all. Instead, the universe could bounce or transition through these regions, continuing in a new form. If that's true, then the end of one universe could be the beginning of another. The Big Crunch could rebound into a new Big Bang. The Big Rip could lead to fragments of space-time budding off into new regions. Even the Big Freeze, if governed by quantum fluctuations, could eventually give rise to new bursts of creation. These ideas are speculative, but they all share a common insight. Endings may not be as final as they appear when seen from within the flow of time. To understand how such rebirths might occur, it helps to look at how quantum physics treats nothingness. In classical physics, empty space is truly empty, a void without matter or energy. But in quantum mechanics, even the vacuum is restless. It seethes with temporary particles that appear and vanish, flickering in and out of existence. These fluctuations are not mere mathematical curiosities, they have measurable effects. The Casimir effect, for example, arises from the energy of the vacuum itself. If this quantum vacuum exists everywhere and always, then even in a universe that seems dead, cold, dark, and empty, there's still potential. Over immense spans of time, those fluctuations could, in theory, produce a region of space where conditions allow for expansion. If such a region appears, it could inflate, creating a new universe, separate from, but born out of, the previous one. This idea, sometimes called eternal inflation, envisions a cosmos where universes continually form within a larger background of quantum space. Our universe, in that picture, is just one bubble among countless others. Each bubble could have its own laws, constants, and dimensions, depending on the conditions that formed it. In such a multiverse, there is no single beginning or end, only transitions between states. A big crunch in one region could feed energy into the quantum background, triggering the birth of new regions elsewhere. A big rip could fragment space-time, each fragment stabilizing into a new universe. Even the quiet stillness of a big freeze could, through a rare quantum fluctuation, spark a new Big Bang. The overall structure would continue indefinitely, with universes forming, expanding, and fading in an endless cycle of creation. This vision changes what we mean by after. If the multiverse exists, then there's always an after somewhere. Even if our own universe becomes uninhabitable, its energy and information could contribute to new worlds. The cosmos as a whole never ends. It only transforms. What we think of as death becomes a form of cosmic recycling. But this idea raises deep philosophical questions as well as scientific ones. If other universes exist, can they ever interact with ours? Could we ever detect their presence? For now, the answer seems to be no. The boundaries between universes, if they exist, are separated by regions expanding faster than light. Any information crossing those boundaries would be lost to us forever. Even so, some cosmologists look for subtle signatures that might hint at such interactions. Collisions between universes, if they happened in the distant past, might leave faint imprints on the cosmic microwave background, tiny irregularities in its otherwise uniform glow. So far, no clear evidence has appeared, but the search continues. Another possibility for what comes after lies not in new universes, but in transformations within this one. Even if expansion continues forever, quantum physics suggests that change never truly stops. Over unimaginable timescales, random fluctuations could create pockets of order in the chaos of emptiness, brief moments when particles and structures spontaneously form. One speculative concept, the so-called Boltzmann brain, imagines a conscious observer arising by chance out of random fluctuations. The odds of this happening are astronomically small, but in an infinite amount of time, even the most improbable events eventually occur. These ideas may sound surreal, but they emerge naturally from the mathematics of entropy and probability. In a universe without an end, where time extends indefinitely, every possible configuration can eventually happen. Even if the big freeze leads to near-perfect stillness, quantum mechanics ensures that absolute stillness is never complete. The vacuum fluctuates, possibilities remain, and creation, in one form or another, continues. If we turn back to the Big Crunch, the notion of continuation is equally compelling. In the classical picture, everything collapses into a singularity, a point of infinite density. But in quantum models, the singularity might be replaced by a bounce. The contraction could slow, reverse, and expand again, producing a new universe from the compressed energy of the old one. Each cycle could leave traces in the fabric of space, subtle imprints that carry information from one universe to the next. We might, in theory, be living in a universe that already followed such a cycle, unaware of the one before it. Some versions of this idea come from loop quantum cosmology, a framework that applies the principles of quantum mechanics to the structure of space-time itself. In these models, space isn't continuous, but made of discrete loops. As the universe contracts, it can't collapse into an infinitely small point. Instead, the loops create a minimum volume, preventing a true singularity. When that limit is reached, the pressure of quantum geometry forces expansion to begin again. In that way, the Big Bang becomes not a beginning, but a bounce, a continuation of a process with no true origin or end. Even the most speculative theories about what comes after have something in common. They all reflect the same principle of persistence. The universe in any form resists absolute nothingness. Whether through quantum fluctuations, bounces, or multiversal branching, something always continues. That idea echoes a theme that appears not just in physics, but in every attempt to describe reality, that existence is never truly erased, only transformed. Of course, all of this remains theoretical. We have no way yet to observe what lies beyond the observable universe, let alone beyond its lifespan. Our data come from light, and light only tells us what has already happened. The future, by definition, remains hidden. Still, the patterns we can see, the laws of energy, the symmetry of forces, the consistency of physics, all suggest continuity. Nothing we know supports the idea of an abrupt end. Even in the most final-seeming scenarios, something endures. For some scientists, this persistence is a comfort. It means that the story doesn't truly end, even if our place in it does. For others, it's a challenge, a reminder that our understanding of time, entropy, and existence is incomplete. Time, as we experience it, is linear. It flows forward, carrying us from one moment to the next. But on cosmic scales, time may not work that way. It may curve, loop, or even branch. Our universe could be one path through a vast landscape of possibilities, with countless others running alongside or beyond it. The idea of after might not mean later, it might mean elsewhere. Somewhere beyond what we can see, beyond what we can measure, space could already be unfolding into new forms, governed by laws that are both familiar and alien. The same quantum seeds that gave rise to our universe could be sprouting others, each with its own constants, its own dimensions, its own version of physics. Some might last only a heartbeat. Others might expand and flourish for trillions of years. Together, they could form an infinite self-renewing cosmos. Not a single universe, but a universe of universes. If that's the case, then the end of our universe is not a failure or a loss. It's part of a larger process of creation. The energy that once formed stars and life here might one day help shape something else, somewhere beyond our reach. The elements scattered by ancient supernovae, the photons released by distant galaxies, the quantum fields that fill space, all of it remains part of the cosmic continuum. The universe doesn't stop, it changes hands. And even if the multiverse remains speculative, there's a simpler truth at its core. Every ending we can imagine, heat death, collapse, dissolution, is also a transformation. The cosmos is not static, it's dynamic by nature. Every law we know describes motion, exchange, evolution. In that sense, even the end of time may simply be another state of motion, one we can't yet describe because we're still within the flow of the current one. There's something quietly profound about that idea. The universe doesn't need to last forever to be infinite. Its infinity lies not in endless duration, but in endless possibility. Whether it fades, falls, or unravels, the potential for something new remains woven into its structure. The same energy that began the universe is still here, spread thin but present, waiting in every particle, every field, every fluctuation. It's difficult to speak of what comes after without using human language, words like beginning, end, rebirth. But those are simplifications. The universe doesn't think in stories. It simply is. It follows the rules that arise from its nature. We give it meaning because we can see patterns, because we can imagine time as a line. But on the scale of the cosmos, meaning itself might be another kind of transformation. The universe doesn't ask why it continues. It just continues. When we look to the far future and wonder what happens next, we're really asking a question about ourselves. What does it mean to exist in something that changes forever? What does it mean to be conscious in a universe that may one day forget consciousness ever existed? These questions are not separate from physics. They're part of it. Every law of nature that governs the motion of galaxies also governs the neurons that allow us to wonder about them. We are part of the same process. Whatever comes after the universe will, in some way, include the trace of everything that came before, including us. And perhaps that's the most lasting answer of all. No matter how far expansion carries us, no matter what form the universe takes after its apparent end, we are not outside it. We are the universe contemplating its own continuation. We are its awareness, its brief flash of self-recognition. Whatever comes after, whatever replaces this structure, will still be connected to that same origin. The cosmos is not something we watch. It is something we are. If there is something beyond the end, it may not be a place or a time. It may simply be the continuation of existence in another form. Energy changing state. Matter dispersing. Patterns reforming. The universe has done this before. It has gone from nothing to everything, from simplicity to complexity, from chaos to order. It could do so again. The question is not whether it will, but how. And as we follow that thought, we return naturally to the present, to this brief moment, this thin slice of cosmic time in which stars still shine, galaxies still form, and life still wonders. The future may stretch beyond imagination, but the present is part of it. The expansion that will one day carry galaxies beyond reach is the same expansion that allows us to look up at them tonight. The energy that drives the cosmos is the same energy that moves through every living being. The end, whatever it is already connected to this moment. So when we think about what comes after, perhaps the most meaningful thing we can recognize is that the universe is never really separate from itself. Every phase, from the Big Bang to the Big Freeze, from the formation of atoms to their dissolution, is part of one continuous process. What comes after isn't waiting in the distance. It's already unfolding right now, in the quiet background of everything we see. How does it feel to be part of this grand unfolding? What does it mean to live on one tiny world, inside a universe that might never truly end? For all the vastness of the universe, for all the billions of galaxies and trillions of stars, there is only one place we know where the cosmos can look back at itself. A small blue world, orbiting an ordinary star in the outer edge of an unremarkable galaxy. When you step outside at night and look up, what you see isn't just light travelling through space. It's history, billions of years old. It's the record of everything that ever happened, written across the sky. And yet, from this one tiny planet, surrounded by the quiet dark, we have managed to ask questions that reach all the way to the beginning and end of time. That might be the strangest thing of all, that the universe, through us, has become aware of its own existence. We are part of the same matter that formed the stars, yet we can stand beneath them and measure their light. The atoms in our bodies were forged in stellar cores, scattered by supernovae, and reassembled by gravity and chemistry into living tissue. Every breath you take contains particles older than the sun. Every heartbeat is powered by the same kind of fusion that once illuminated the earliest galaxies. In that sense, when we study the universe, we're studying ourselves. We are the result of its long expansion, the temporary arrangement of matter, that can notice its own impermanence. When you look at the night sky, it's easy to feel small. The distances are so great that they seem beyond comprehension. Light from the nearest star takes years to arrive. Light from distant galaxies has travelled for billions of years. Some of the photons that reach your eyes tonight began their journey before Earth existed. They have crossed the entire history of the universe to meet you here. The scale of it all is so enormous that our own existence feels fragile. A brief flicker of consciousness surrounded by eternity. But that fragility doesn't make us insignificant. It makes us remarkable. Every measurement, every observation, every piece of knowledge we have about the cosmos comes from the same place. A mind capable of curiosity. From this single planet, we've managed to map the shape of space, to trace the age of time, and to calculate the motion of galaxies millions of light years away. We've built instruments that can detect the faint afterglow of the Big Bang, the ripples of space-time caused by colliding black holes, and the gravitational lensing of distant clusters. We've taken the oldest light in existence and turned it into information. For all the distances we can't cross, our reach is astonishing. It's worth remembering that for most of human history, none of this was known. The sky was a mystery filled with patterns but without explanation. We saw cycles, the rising and setting of stars, the phases of the moon, the passing of seasons, but we didn't know what they meant. It was only recently, in the last few centuries, that we began to understand the sky as a physical place, governed by laws we could describe. The same physics that governs falling apples also governs orbiting planets. The same light that illuminates the sun travels from galaxies beyond imagination. The same gravity that holds you to the ground sculpts the shape of space-time itself. And now, from this small world, we can describe the entire visible universe. We know that it began about 13.8 billion years ago. We know that it is expanding, that galaxies move apart, and that this expansion is accelerating. We know that the stars will one day die, and that the future will be long and quiet. Yet, in knowing these things, we're not diminished by them. We're part of the process we describe. The same laws that govern galaxies also govern our thoughts. We are, in the most literal sense, made of the universe's curiosity. Sometimes people ask what the purpose of it all might be, why the universe exists, why it expands, why there is something rather than nothing. Science doesn't give final answers to those questions, but it shows us that purpose and existence are not necessarily separate. The universe doesn't need a reason to exist any more than a tree needs a reason to grow. It simply follows from its nature, and within that process, life arises as one of its ways of exploring itself. Consciousness is not outside the universe. It's one of the ways the universe becomes aware of its own unfolding. That perspective can be both comforting and humbling. We are small, yes, but we are connected to everything. The calcium in your bones, the iron in your blood, the carbon in your cells, all of it was born in stars. The energy that sustains you each day came from the fusion of hydrogen in the heart of the sun. The same expansion that carries galaxies apart also carries the air around you, the waves across the sea, and the photons that light your room. You're not separate from the cosmos. You're one of its expressions, one of its passing patterns. When we think about the universe ending, in cold, in collapse, or in disintegration, it's easy to feel a kind of melancholy. Everything we know and love seems temporary. But temporariness is what allows the universe to exist in the first place. Without change, there could be no stars, no chemistry, no life. Every atom in your body has been through countless transformations, passing through stars, dust clouds, and other forms before becoming part of you. And even after you're gone, those atoms will continue their journey, joining new structures, perhaps new forms of life, perhaps new worlds. You are part of an unbroken chain of transformation that began long before you and will continue long after. There's something quietly profound about realizing that we are the brief intersection of cosmic history and self-awareness. The universe spent billions of years creating the conditions for thought, for perception, for memory. Out of all that time, we exist now, in this moment, able to reflect on where we came from and where everything might be heading. We might not be able to change the fate of the cosmos, but we can understand it. And that understanding is itself a kind of participation. It's strange to think that, in the far future, the traces of our existence may vanish. The light from our sun will fade, the galaxies will drift away, even the atoms that make up this world will one day be scattered or transformed. There will be no evidence left that we were here, but the fact that we existed, that the universe once contained beings capable of asking about its fate, changes the meaning of that fate. The cosmos has already produced awareness. It has already looked at itself and wondered why. That single act ensures that its story includes meaning, even if meaning itself is temporary. From our perspective, the universe feels vast beyond comprehension, but that immensity is what allows moments like this to exist. The same processes that began in the first seconds of the Big Bang eventually made it possible for complex chemistry to arise, for planets to form, for light to evolve into thought. Every conscious being is a local interruption in entropy, a place where the universe briefly remembers its own order before returning to equilibrium. The more we understand that, the more miraculous existence itself becomes. Sometimes, late at night, it's possible to feel that awareness directly. The hum of the universe becomes personal. The air feels ancient. The light from the stars seems less like decoration and more like history reaching out. In those moments, the distinction between out there and in here begins to fade. The universe isn't distant, it's immediate. It's in every cell, every breath, every heartbeat. You're not in the universe. You are the universe, arranged for a while in a way that can ask about itself. It's worth pausing on that thought. The universe will continue long after we're gone. It will expand, evolve, and perhaps eventually fade. But right now, in this small corner of space, it has found a way to think, to feel, to create art and music and science. It has found a way to imagine its own end and to wonder what comes after. In that sense, the human moment is not small at all. It's the moment when the cosmos becomes conscious of its own story. All our tools, telescopes, equations, theories, are extensions of that awareness. When astronomers measure redshift, they're not just studying light. They're listening to the echo of the universe's first breath. When physicists calculate the expansion rate, they're mapping the rhythm of space-time itself. Every observation is a conversation between the part and the whole. We ask, and the universe answers, not with words, but with patterns, with spectra, with motion, with light. And each time we interpret those patterns, we add another layer to the universe's own self-understanding. From a distance, the Earth is a fragile thing, a small blue circle floating in the dark. But from up close, it's rich and vibrant, filled with life that draws energy from the same laws that govern galaxies. Our planet is both insignificant and essential. Without it, the universe would still exist, but without it, the universe would never have known itself this way. Every living thing, from the simplest cell to the most complex mind, participates in that act of awareness. The cosmos may not care, but it experiences itself through us nonetheless. When we think about the end of the universe, we're not really imagining an external event. We're imagining the loss of that awareness. We're imagining the silence that follows once there is nothing left to wonder. But maybe that's the wrong way to think about it. Awareness, like energy, doesn't disappear. It transforms. Every mind, every perception, every moment of consciousness contributes to the ongoing unfolding of reality. We are part of a continuum that may take new forms in the future, even if we can't imagine them. Perhaps far in the future, long after the stars have gone dark, other kinds of awareness will arise, forms that don't depend on warmth or light, but on subtle fluctuations in quantum fields or patterns in the last traces of radiation. The universe has already proven itself capable of extraordinary creativity. There's no reason to believe that creativity stops at any particular boundary. But even if no new life ever appears, the story we've already written into the cosmos remains. The radio waves we've sent, the light from our cities, the signals from our spacecraft, they all travel outward, crossing the emptiness, carrying traces of our existence into the wider universe. They may never be received, but they are part of the universe now, embedded in its expanding fabric. The same is true of our thoughts and discoveries. Every insight changes how the universe understands itself, if only through us. It's easy to forget that, for all the talk of cosmic scales and distant futures, we are living at an extraordinary time. We exist when the sky is still bright, when galaxies are still visible, when the evidence of the Big Bang is still detectable. In the far future, observers, if any remain, will no longer be able to see those signs. The cosmic microwave background will fade below detectability. The expansion will carry distant galaxies beyond reach. The universe will grow dark and its origins will be hidden. We right now live in the only era when the universe can still see itself clearly. We are witnesses to its middle age, the point of balance between birth and disappearance. That makes our moment precious, not because it's permanent, but because it's temporary. We exist between the glow of the beginning and the silence of the end. We are the brief light in between. That light is not just physical, it's intellectual, emotional, creative. It's the light of awareness. And though it may fade, its existence changes everything. Once the universe has known itself, even briefly, it has done something irreversible. It has turned matter into meaning. So when you look up at the stars, try to remember that you are looking at the same process that made you. You are not beneath the universe, you are within it. The atoms in your eyes are reading the light of ancient suns. The thoughts in your mind are shaped by the same physical laws that move the galaxies. The distance between you and the edge of the universe is not emptiness, it's continuity. You're connected to it all, not by belief, but by fact. The human moment, then, is more than a point in time. It's a realization. It's the recognition that existence, awareness, and the cosmos are not separate. The universe has spent billions of years preparing the conditions for complexity, and now, for a brief instant, it can see, feel, and understand through us. That is its achievement. That is our place in the story. Through expansion, through fading light, through whatever transformations lie ahead, we remain part of it. The same forces that will one day end the stars are the forces that made us possible. The same laws that describe the universe's death also describe its birth. There is no separation. There never was. The question that remains is not how the universe will end, but how we live within it now. How we use this fleeting moment of clarity, this rare opportunity to see ourselves as part of something immeasurable. If you followed the universe this far, through its first moments of expansion, through the birth and death of stars, through the possibilities of freezing, collapsing, or unravelling, you've already crossed nearly all of time. You've walked from the beginning to the end and found that there may be no such thing as either. The universe doesn't really start or finish. It changes. It moves through forms. And somewhere inside all of that, you exist. A small consciousness suspended between the infinite past and the infinite future, aware of both, wondering what it means to be here at all. When people talk about the expansion of the universe, it can sound distant, abstract, too large to feel. Space stretching between galaxies is hard to imagine because we live within gravity's domain, where the pull of the Earth keeps everything near. But the expansion isn't only out there, in the deep cosmic void. It's everywhere. It's in the photons that leave the sun and reach your skin. It's in the background radiation that fills every cubic centimetre of space around you. It's even in the subtle drift of time, the way the present moves forward, carrying everything along. Expansion isn't just a property of the universe, it's its nature. And because you are part of the universe, it happens within you too. Every atom in your body, every molecule, was once part of a larger system, broken apart and rearranged through the same cosmic processes that shaped galaxies. The carbon in your breath, the oxygen in your blood, the calcium in your bones, all of it has travelled through cycles of expansion. You're a small continuation of the same unfolding that began billions of years ago. That thought is simple, but profound. The universe isn't something you observe, it's something you are. When you breathe, you exchange energy and matter with the world around you. When you think, electrical signals move through patterns of atoms that once belonged to stars. Every moment of awareness is built from the same physical laws that drive cosmic evolution. You're not watching the universe expand, you're participating in it. The motion of galaxies and the rhythm of your heart are parts of one continuous process. It's easy to forget that connection in daily life. The human world moves quickly, filled with noise and activity, while the universe seems silent and unchanging. Yet they are not separate worlds. The stillness of the sky and the movement of your thoughts are expressions of the same structure. The curvature of space that bends starlight also guides the flow of water, the fall of rain, the orbit of your planet around the sun. Every action, from the largest to the smallest, follows the same laws. The cosmos is not distant, it's intimate. It lives through you. If you could slow down time enough, if you could stretch a single second to last 1,000 years, you might see the expansion happening around you. You would see galaxies drift infinitesimally apart, wavelengths of light stretching, the cosmic background growing cooler. You would see the Earth move through space, the sun spiral around the center of the Milky Way, and the Milky Way itself move through the dark fabric of the cosmos. You would see that nothing, not even the emptiest void, stands still, and yet within that constant motion there is calm. The laws that govern everything are stable. Gravity, electromagnetism, the nuclear forces, they've remained unchanged for over 13 billion years. That consistency is what allows the universe to evolve with such quiet precision. It's what allows atoms to form, stars to shine, planets to orbit, and life to arise. When you think about it, stability and change are not opposites. They are partners. The universe stays the same by changing, maintaining balance through transformation. That balance extends to you. Every cell in your body is constantly replaced, rebuilt from materials that come from outside. Food, water, air. Every breath changes you slightly. You're not the same person you were a few years ago, or even a few moments ago. The atoms that make you are borrowed, and they will return to the universe when your time ends. But in this moment, you are the universe gathered into a specific pattern, a temporary arrangement that can perceive itself. You are the cosmos, aware of itself however briefly. When you think of it that way, expansion becomes less about distance and more about awareness. The universe isn't growing into something else, it's revealing more of itself. Every new star that forms, every new life that begins, every new question asked is part of that revelation. The expansion of the universe is also the expansion of understanding. Each discovery, each act of perception, stretches the boundary of what the universe knows about itself. You are one of those acts. There's a kind of comfort in recognizing that you're not outside this process. When you look up at the night sky, you're seeing not just stars, but the ongoing story of change. The light that reaches you has travelled for millions or billions of years, passing through regions of expanding space, crossing epochs of cosmic evolution. By the time it reaches your eyes, it carries not just information, but connection, a reminder that you're part of the same continuum. The light that enters you becomes part of you. The photons that strike your retinas release energy, and that energy becomes thought. The universe looks at itself through your vision. Even in its most distant future, that connection will remain. When the stars are gone and the galaxies fade beyond the horizon, the laws that allowed awareness to exist will still be there, written into the structure of space itself. Energy may be spread thin, but it will not vanish. Matter may decay, but the fields that define it will persist. And even if no consciousness survives to witness it, the capacity for order, for pattern, for complexity will remain embedded in the potential of existence. The universe's expansion is not only a movement through space, but through possibility. That is what it means when we say the universe still expands within you. It's not a metaphor. It's the recognition that the same creative process that shaped the cosmos continues through your existence. You carry its momentum, you inherit its curiosity, you express its laws with every breath. The expansion isn't something that ended after the Big Bang. It's ongoing, unfolding through stars, through life, through thought. The act of wondering what expansion means is itself part of that expansion. If you take a moment to imagine the very beginning, the instant of the Big Bang, it's almost impossible to picture. There was no space, no time, no outside to contain it. Everything that would ever exist was compressed into a single, dense state. Then, for reasons we still don't fully understand, expansion began. It wasn't an explosion in space. It was the creation of space itself. Every direction became outward. Every point became a beginning. That same expansion continues now, carrying galaxies away and stretching light across the void. And it continues through you, in smaller, quieter ways. Every thought, every act of creation, every moment of understanding is a continuation of that first movement. The unfolding of something into something more. Even if the universe one day reaches an end, in silence, in collapse, or in dissolution, the expansion doesn't truly stop. It changes form. The flow of time becomes something else, but the principle remains. Transformation, movement, continuity. That's what the universe does. It changes, it evolves, it becomes. When you feel small beneath the night sky, remember that you are not separate from it. You are the product of billions of years of cosmic history. The hydrogen in your body was born when the universe was young. The heavier elements were forged in the hearts of dying stars. The energy that fuels your body once travelled across the cosmos as starlight. You are the result of expansion, not apart from it. When you think, the universe is thinking. When you feel, the universe feels. When you exist, the universe expresses itself in a way that it never has before. That may be the quiet truth at the heart of everything we've learned, that the universe is not only vast and mysterious, but participatory. It's not a backdrop, not an indifferent void. It's an active process of creation and awareness, and we are one of its brief forms. You don't need to travel to the edge of space to be part of it. You already are. Every breath, every thought, every moment is a continuation of the same unfolding that began long ago and will continue long after. If the universe could speak, it would not tell you that you are insignificant. It would tell you that you belong. You belong because you are made of it. You belong because you are what it has become. The expansion of the universe is not something happening around you. It is happening through you. You're one of the ways it expands, in complexity, in awareness, in meaning. And perhaps when the stars have gone out and the galaxies have drifted beyond reach, when all that remains is the faint hum of the cosmos cooling in the dark, the trace of that belonging will still echo somewhere, not as sound, but as the persistence of existence itself. Because the universe does not vanish, it continues in every form it has ever taken. And you, as one of those forms, are part of that continuation. So when you look up at the night sky, or close your eyes and imagine it, remember that everything you see, everything you are, is the universe in motion. The light that began its journey billions of years ago arrives now, and in receiving it, you complete that journey. You're not apart from the expansion, you're its witness, its participant, and its expression. The universe still expands within you, in every breath, in every thought, in every moment you wonder what it all means. Its story is your story, written in atoms, in time, and in awareness. It will go on long after you, just as it began long before you, and in that endless continuation it remains whole. The expansion never stops. It moves quietly, without hurry, carrying everything forward. And if you listen closely, in the spaces between thoughts, in the stillness of the dark, you can feel it, the slow, steady unfolding of reality itself, reaching out in every direction, including within. That's all the universe has ever done. It expands, it evolves, it becomes, and for a short while through you, it knows that it does. Thank you for being here tonight, for letting your thoughts drift across the stars, for giving yourself time to breathe and wonder. The universe is still expanding, and so are you. Every moment of curiosity, every quiet question, every heartbeat is part of that same motion. If this helped you slow down, if it made you feel a little smaller in the best possible way, then let yourself rest in that feeling. You don't need to solve the cosmos tonight. You're already part of it. You always have been. If you'd like to stay on this journey, through galaxies, through time, through everything that connects science and stillness, you can join me here again. Subscribe, follow, or simply come back when you need a place to think slowly. Until next time, take care of yourself. Look up when you can, and remember, even when everything seems still, the universe is quietly moving forward, and so are you. Good night.